Chevrolet, Hyundai, and Nissan are three of the biggest names in the global auto industry, and building their cars is a massive undertaking. Inside their factories, cutting-edge robotics and complex assembly lines work together to turn raw steel and parts into fully finished vehicles. Today we're going inside to see exactly how these cars are made from start to finish. Before a Chevrolet ever rolls out of a dealership lot, it begins its life in a process that is both highly technical and deeply coordinated, involving years of preparation before a single part is even manufactured. The journey starts in Chevrolet's design and engineering departments, where teams of designers, mechanical engineers, and manufacturing planners work together to create not just the look of a vehicle, but the exact way it will be built. The earlier stages are dominated by design feasibility. Engineers ensure that the proposed vehicle shapes, curves, and mechanical layouts are compatible with large-scale manufacturing techniques. This includes determining how each body panel will be stamped, how wiring harnesses will be routed, and how components will be positioned for both performance and serviceability. It is here that design for assembly comes into play. In every element must be optimized for efficient installation without compromising quality or safety. This is especially critical for Chevrolet, which produces a wide range of models, from compact sedans to full-size trucks, each with very different manufacturing needs. Once the design is finalized, manufacturing engineering takes the blueprint and transforms it into a step-by-step factory plan. This involves defining which machines, robots, and tooling will be used at each stage of production, how workers will interact with them, and how the line will be sequenced to handle multiple model variations. Many Chevrolet plants are designed for mixed model production, meaning that a pickup truck and a crossover SUV could be assembled back-to-back on the same line. This requires extremely precise scheduling and tooling flexibility. The process begins with raw material arrival, particularly steel and aluminum sheets that form the vehicle's structural backbone. These materials arrive at the stamping plant in the form of enormous coils, each weighing many tons. The coils are unrolled, cut into blanks, and fed into massive stamping presses. These presses, some of the largest machines in the automotive world, shape the metal into fenders, roofs, doors, and other body panels using dies that weigh several tons themselves. Each panel typically goes through several stamping stages, moving from a rough shape to precise final contours. During stamping, dimensional accuracy is paramount. Even a fraction of a millimeter of error can cause alignment issues later in the build. Chevrolet uses automated inspection systems to verify each panel's geometry, rejecting or recycling any piece that fails to meet exact standards. This quality control in the stamping phase prevents costly rework later down the line. From stamping, the panels move into the body shop. Here, the flat, separate pieces are joined together to form the body in white, the term for the bare, unpainted vehicle shell. This process is dominated by robotic spot welding, where arms with welding guns move in perfectly choreographed sequences to fuse the panels together. The body shop operates on a combination of fixtures and jigs that hold each piece in precise alignment, ensuring structural strength and proper fit. The floor pan is laid down first, then side panels, roof structures, and reinforcements are added in a sequence determined by both structural integrity and manufacturing efficiency. Chevrolet plants use hundreds of welding robots, but human oversight remains critical. Skilled technicians monitor the welding cells, handle complex welds in tight spaces, and conduct random sample checks to confirm that weld penetration and positioning meet specifications. In some areas, adhesive bonding is used alongside welding to increase rigidity and reduce noise, vibration, and harshness. After the body is fully assembled, it undergoes detailed dimensional checks using coordinate measuring machines or laser scanning systems. If all is within tolerance, the body in white moves to the paint shop. The paint process is one of the most controlled environments in the factory, as even a speck of dust can mar the finish. The first step in painting is cleaning and pre-treatment. The body is submerged in a series of chemical baths to remove grease, oils, and contaminants. A phosphate coating is then applied to improve corrosion resistance. This is followed by the electrophoretic deposition, or E-coat, where the body is dipped in a charged primer bath that ensures complete coverage in every nook and cavity. The E-coat is then baked to cure it into a durable base layer. Once primed, the body passes through sanding and inspection areas before moving to the color base coat booths. Chevrolet's paint lines often use robotic spray arms programmed to follow complex paths that ensure an even application over curves, edges, and recessed areas. Some vehicles receive two-tone paint or special finishes, requiring masking and multiple spray cycles. The base coat is followed by a clear coat, which provides gloss and protection from UV rays and environmental wear. Each coat is baked in ovens to cure it, hardening the finish for durability. After the final paint cure, the body emerges looking complete on the outside, but it is still just a shell with no functional systems. This is where the trim and chassis assembly phases begin. The painted bodies move onto the trim line, where workers and robots install interior components in a carefully sequenced order. Wiring harnesses are routed through the body, HVAC ducting is fitted, and dashboards are installed as complete units. Seats, carpets, door panels, and center consoles are added, with quality checks at each station. Parallel to this, in another part of the plant, chassis sub-assemblies are being prepared. Engines, transmissions, front and rear suspension units, exhaust systems, and brake assemblies are mounted onto subframes. This pre-assembly ensures that when the time comes, the drivetrain can be installed into the body quickly and accurately. With the major mechanical and trim installations complete, the Chevrolet moves into the final assembly verification and testing phase. At this point, the vehicle is fully recognizable, but its systems have yet to prove themselves under controlled evaluation. This stage is where the factory shifts its focus from building to validating. One of the first stops is the wheel alignment station. Using laser-based or camera-guided systems, technicians check the alignment angles for each wheel: camber, caster, and toe. Proper alignment is essential not only for safe handling, but also for tire longevity and fuel efficiency. Adjustments are made at the suspension components until all readings are within Chevrolet's specified tolerances. These specifications are tied to each model's unique suspension geometry, ensuring consistent road feel across every unit. Next, the vehicle proceeds to the fluid fill and system pressurization stage. While many fluids, such as engine oil, brake fluid, and coolant have been partially filled earlier in the assembly process, this step ensures that all are topped off to exact levels and that the systems are free of leaks or trapped air. For braking systems, pressure testing and bleeding are performed to guarantee firm pedal feel and consistent stopping power. The fuel system is also pressurized and checked for leaks, as even minor seepage can create both safety and emissions compliance issues. Then comes one of the most exciting moments on the factory floor: the first engine start. At a dedicated startup station, the technician engages the ignition, bringing the Chevrolet's powertrain to life for the very first time. The engine's idle is monitored closely for smoothness, proper fuel-air mixture, and the absence of unusual noises or vibrations. The onboard diagnostic system is immediately scanned to ensure no fault codes are present. If a code does appear, it is addressed on the spot before the car moves on. After the initial start, the vehicle advances to the rolling road test, also known as the dynamometer station. Here, the car's drive wheels rest on large rollers that simulate real road resistance. A trained operator runs the vehicle through different speed ranges, gear changes, and acceleration profiles, while onboard sensors monitor performance. For automatic transmissions, shift smoothness is evaluated. For manual transmissions, clutch engagement and gear selection are tested. Braking performance is also checked under controlled simulated loads. This phase helps confirm that the powertrain, drivetrain, and braking systems are functioning exactly as intended before the vehicle ever touches pavement outside the plant. Following the rolling road, the vehicle undergoes an emissions and noise compliance check. In the emissions booth, exhaust gases are captured and analyzed by high-precision equipment to ensure they meet the regulatory standards of the destination market. For noise compliance, sound level meters measure exterior and sometimes interior noise levels under specified conditions, ensuring that they fall within acceptable limits for both legal compliance and customer comfort. With these mechanical verifications complete, attention shifts to fine detailing and final adjustments. At the fit and finish inspection stations, experienced workers examine every panel gap, every seam, and every interior surface for perfection. Door alignment, hood closure effort, and trunk latch operation are all tested. Inside the cabin, all switches, controls, lighting, and infotainment functions are checked one by one. Even the alignment of stitching on seat upholstery can be grounds for rework if it fails to meet the brand's aesthetic standards. One of the more dramatic quality checks is the water leak test. The Chevrolet is driven into a sealed booth equipped with high-pressure spray nozzles that douse the vehicle from all directions, simulating heavy rainfall and road spray conditions. After several minutes, the vehicle is opened and inspected for any trace of water inside. Any leak, no matter how minor, is immediately repaired, often by replacing seals or adjusting window or door fitment. Once the car passes the water test, it proceeds to the underbody inspection area. Here, the vehicle is lifted and technicians check for proper routing of hoses, cables, and exhaust components. Protective coatings are examined to ensure full coverage, especially in corrosion-prone areas such as wheel wells and chassis rails. This stage is also a final safeguard for identifying loose fasteners or missing clips. The last stage before leaving the assembly building is the final audit. This is a comprehensive evaluation combining visual, functional, and performance checks into one ultimate sign-off process. The audit team often includes some of the most experienced personnel in the plant, and their approval is a requirement before a car can be released. Every system, from headlights to climate control, is tested again, and any deviation from perfect operation is corrected immediately. Once signed off, the Chevrolet is prepared for shipment. Protective plastic films are applied to painted surfaces most vulnerable to transit damage, such as hoods, roofs, and door edges. The interior is covered with disposable mats, seat covers, and steering wheel wraps to keep it pristine until delivery. From here, the vehicle enters the shipping yard, where it is grouped with others bound for the same distribution points. Domestic-bound vehicles are loaded onto specialized car carrier trucks with wheel straps securing them in place. For longer domestic routes, some are shipped by rail in enclosed auto racks. Export vehicles are driven onto roll-on/roll-off ships for overseas transport, where they are secured in dense, organized rows for the voyage. Upon arrival at regional distribution centers or directly at dealerships, each Chevrolet undergoes a pre-delivery inspection to ensure that transport has not caused any damage or alignment issues. Fluids and tire pressures are rechecked and protective coverings are removed. If accessories ordered by the customer were not installed at the factory, they may be fitted at this stage. Only after this chain of precise manufacturing, rigorous testing, and careful transport does the vehicle reach the customer. From the initial design to the moment the keys are handed over, every Chevrolet is the product of thousands of coordinated actions, each performed to uphold the brand's standards of reliability, performance, and quality. Long before a Hyundai rolls out of a showroom or cruises down a highway, it begins life in a complex and highly synchronized industrial process that blends advanced automation with skilled human craftsmanship. The journey starts far from the factory floor, in Hyundai's design and engineering centers, where teams of stylists, mechanical engineers, safety experts, and manufacturing specialists collaborate to transform a concept into a buildable reality. This early collaboration is critical. It ensures that the car's shape, structure, and systems are not only aesthetically pleasing and mechanically sound, but also feasible to mass produce. Every curve of the body is analyzed for how it will be stamped from metal sheets. Every bracket and mounting point is evaluated for efficient installation, and every wiring harness route is mapped to avoid interference with other systems. Hyundai applies design for manufacture principles from the outset, reducing assembly complexity and ensuring consistent quality. Once the design is finalized, the manufacturing engineering teams take over. Their task is to translate that design into a precise, step-by-step production plan that integrates seamlessly into Hyundai's global manufacturing network. This means specifying which machines, robotic systems, and fixtures will be required, how the assembly line will be arranged, and what level of automation each task demands. Many Hyundai plants are set up for mixed model production, allowing sedans, SUVs, and even electric vehicles to be built on the same line. This flexibility demands exceptionally detailed scheduling and tooling strategies. The process physically begins with the arrival of raw materials. The backbone of most Hyundai vehicles is steel, often high strength, and sometimes blended with lightweight aluminum alloys for weight savings. These materials arrive in the form of massive coils, each weighing several tons, delivered by rail or truck directly to the stamping plant. Before the first press stroke, these coils are unrolled, cut into flat blanks, and fed into enormous stamping presses. These presses are monumental machines capable of exerting thousands of tons of force. They shape the flat metal sheets into body panels, such as fenders, roof sections, hoods, and door skins. Each panel typically passes through a series of dies, the first forming a rough shape, the following ones refining it to exact tolerances. Hyundai's dies are precision engineered and often swapped out by automated die changing systems to minimize downtime between production runs. Dimensional accuracy at this stage is essential. Even a slight misalignment in a stamped panel can cause compounding fitment problems later. To prevent this, Hyundai employs automated vision systems and laser scanners that inspect each panel as it leaves the press. Any panel outside specification is sent for recycling, with the metal returned to the supply chain to minimize waste. From stamping, the panels move into the body shop, a vast, robot-dominated hall where the skeletal structure of the car is assembled. Here, the flat pieces are transformed into the three-dimensional form of the vehicle in a process known as body-in-white assembly. This stage is dominated by robotic spot welding, with articulated arms, moving in carefully choreographed sequences to fuse panels together at hundreds of points. The process starts with the floor pan, onto which side frames, roof rails, and bulkheads are positioned and clamped into place by large jigs. These jigs ensure precise alignment so that every vehicle matches the dimensional blueprint exactly. Additional reinforcements are added at structural stress points, such as the pillars between the doors and the crash-absorbing sections at the front and rear. Although robots do the majority of welding, skilled human operators remain essential in the body shop. They handle welds in areas where robotic arms cannot easily reach, inspect the quality of robotic welds, and make fine adjustments to ensure panel gaps and alignment stay within tolerances. In some Hyundai models, structural adhesives are applied alongside welds to increase rigidity and reduce noise, vibration, and harshness in the finished car. Once the body shell is fully welded, it undergoes a dimensional inspection. This involves laser measurement systems or coordinate measuring machines that scan key reference points to ensure that the body conforms to the exact design specifications. Any deviation, even as small as a millimeter, can lead to problems fitting doors, glass, or interior components later. When the body passes inspection, it proceeds to the paint shop, one of the most meticulously controlled environments in the entire factory. The paint process is highly sensitive to dust, humidity, and temperature, so the paint shop is sealed and climate controlled. Before painting begins, the body is cleaned and pre-treated in a series of immersion baths. These remove oils from stamping and welding, apply a corrosion-resistant phosphate layer, and prepare the surface for primer adhesion. Following pre-treatment, the body is submerged in an electrically charged primer bath in a process called electrophoretic deposition, or e-coating. This ensures that primer reaches even hidden cavities, providing a uniform anti-corrosion layer. The body is then baked in an oven to cure the coating into a hard, protective shell. Next comes surface preparation. Technicians and automated sanding units smooth the primed surface, removing any tiny imperfections. The body then enters the base coat booths, where robotic arms apply the vehicle's chosen color in ultra-fine, even layers. For certain models, multi-coat or two-tone paint schemes require masking and additional spray cycles. After the base coat, a clear coat is applied to give gloss and long-term UV and chemical resistance. Each coating layer is cured in a controlled temperature oven to ensure hardness and durability. When the body emerges from the paint shop, it looks like a complete vehicle from the outside. But it is still just a shell. No drivetrain, no interior, and no wiring. This is when it moves to the trim and chassis assembly areas, where it truly begins to take on life. The first steps in trim assembly involve installing insulation and wiring. Sheets of sound-deadening material are placed strategically in the floor, doors, and bulkhead areas to reduce road and engine noise. Pre-assembled wiring harnesses are then routed through the vehicle, connecting future components such as lights, sensors, the infotainment system, and power accessories. These harnesses are secured with clips and ties to prevent rattles and wear over years of use. While the wiring is being installed, HVAC ducting and other hidden systems are fitted. Then comes the dashboard, which often arrives as a complete module from a supplier. Installing the dash is a delicate process, requiring alignment with mounting points and simultaneous connection of numerous wiring plugs. After the dashboard, seats are installed, bolted into the floor, and connected to their respective power or heating controls if equipped. Meanwhile, in a separate section of the plant, chassis and drivetrain components are being assembled into a single underbody module. This includes the engine, transmission, front and rear suspension units, exhaust system, and sometimes the steering assembly. Hyundai uses modular assembly techniques so that this entire unit can be brought to the body in one coordinated step. That step is known as the marriage, and it is one of the most visually striking moments on the assembly line. The painted body shell is suspended slightly above the moving chassis unit, and then the two are lowered and joined together. Bolts are torqued to precise specifications, linking the engine, drivetrain, and suspension to the body. Once the marriage is complete, fluid lines, electrical connections, and control linkages are secured between the body and chassis. This is followed by glazing, installing the front and rear windshields and side windows. High-strength adhesives bond the glass to the frame, contributing to both structural rigidity and weather sealing. By this stage, the Hyundai is a complete, self-contained unit, but it must undergo rigorous testing, adjustment, and final detailing before it is ready to leave the factory. With the body and chassis joined and the major mechanical systems in place, the Hyundai enters the final stages of production. A series of detailed inspections, dynamic tests, and finishing touches that ensure it meets both regulatory standards and Hyundai's own quality benchmarks. This part of the process is just as critical as stamping or welding because it determines whether the car will leave the factory flawless or require rework. The first stop is often the wheel alignment station. Using laser-guided or camera-based systems, technicians check the vehicle's suspension geometry, ensuring that the camber, caster, and toe of each wheel match precise factory specifications. Proper alignment not only affects handling and stability, but also determines tire wear and fuel efficiency. Adjustments are made by trained workers using specialized tools, often within a tolerance of a fraction of a degree. From alignment, the vehicle moves to fluid fill and system pressurization. Even though some fluids, such as engine oil or coolant, may have been partially filled earlier in the assembly, this stage ensures all systems are topped to exact levels. The brake and clutch systems are bled of any trapped air, guaranteeing consistent pedal feel. The air conditioning system is charged with refrigerant, and the fuel system is pressurized to check for leaks. In hybrid or electric models, the high voltage battery systems are also energized and checked for correct function. One of the most significant milestones comes next: the first engine start. At a dedicated station, a technician initiates the ignition sequence or engages the start button. The powertrain roars or hums to life for the very first time. While this moment has a certain ceremonial feel, it is primarily a diagnostic test. Sensors and the onboard diagnostic system are immediately scanned for error codes, while technicians listen for any abnormal sounds and monitor idle stability. Any fault detected is addressed immediately before the car progresses. Following the initial start, the Hyundai is driven onto a rolling road dynamometer, a sophisticated test rig with large rollers beneath the wheels. Here, the vehicle's drivetrain is run through a series of simulated driving conditions. Technicians shift through gears, accelerate, decelerate, and brake, all while sensors record performance metrics. This test checks everything from transmission shift quality to ABS functionality. For electric and hybrid vehicles, regenerative braking performance is also verified. The dynamometer can simulate different road loads, allowing Hyundai to ensure the vehicle responds correctly in both light and heavy driving scenarios. Next, the vehicle enters an emissions and noise compliance station. The exhaust system is connected to high-precision analyzers that measure levels of pollutants such as carbon monoxide, hydrocarbons, and nitrogen oxides, ensuring compliance with the environmental regulations of the target market. Noise testing is also performed, measuring sound levels both outside and sometimes inside the cabin to confirm they meet legal and brand comfort standards. Once mechanical and emissions checks are complete, the Hyundai proceeds to the fit and finish inspection area. This is a zone where highly trained quality inspectors meticulously examine the car's exterior and interior for even the smallest imperfections. Panel gaps are measured with gauges, paint surfaces are inspected under bright, angled lighting to reveal any blemishes, and all interior features are tested for correct operation. If a trim piece is misaligned by even a millimeter, it is corrected on the spot. One of the most important tests at this stage is the water leak test. The car is driven into a sealed chamber fitted with high-pressure spray nozzles, which bombard it with water from all angles to simulate heavy rainfall and road spray. After several minutes, technicians open the doors, trunk, and hood to inspect for any signs of moisture inside. Leaks are unacceptable, so any that are found trigger immediate sealing repairs or component adjustments. Underbody inspection follows, with the vehicle lifted on a hoist so workers can check that exhaust systems, fuel lines, brake hoses, and electrical cables are correctly routed and securely fastened. Protective coatings applied earlier in the build are examined for complete coverage, especially in high corrosion areas like wheel wells and chassis cross members. The final audit is the last checkpoint before a Hyundai can be cleared for shipment. This audit is a condensed but highly rigorous version of all prior tests. Inspectors cycle through every electrical control, verify all lighting and warning systems, and ensure the climate control works in heating and cooling modes. They also test locking systems, window regulators, mirrors, infotainment units, and safety features like airbags through diagnostic systems. The goal is to confirm that the car leaving the factory is indistinguishable in quality from any other unit of the same model, regardless of production date. Once the final audit is passed, the car moves to the shipping preparation area. Protective films are applied to vulnerable painted surfaces such as the hood, roof, and trunk lid to guard against minor scratches or debris during transport. Interior surfaces such as seats and steering wheels are wrapped with disposable covers. The vehicles are then driven to the factory's dispatch yard, a vast parking area organized by destination. Here, they are scanned into Hyundai's logistics system using their unique vehicle identification numbers. This tracking system links each car to its market, dealer, and production details. Domestic shipments are typically loaded onto multi-deck car carrier trucks, secured with wheel straps to prevent movement. For longer domestic journeys, rail transport in enclosed auto racks may be used. Vehicles bound for export markets are moved to ports, where they are driven onto roll-on/roll-off ships. These massive vessels function like floating parking garages, with cars parked in tight formation and secured for the ocean voyage. Once at their destination country, the vehicles undergo customs clearance before heading to Hyundai's regional distribution centers. Here, a process called pre-delivery inspection, or PDI, is performed. This includes removing protective coverings, checking fluid levels and tire pressures, and confirming no damage occurred during transport. Any market-specific adjustments, such as headlight alignment or software settings, are made at this stage. From the distribution center, the cars are delivered to dealerships, where a final light inspection is carried out before they are placed on display or prepared for customer delivery. When the new owner takes the keys, the journey that began with raw steel coils and a concept drawing is complete. Though for Hyundai, the feedback loop from customer to factory continues, helping refine the next generation of vehicles. Before a Nissan vehicle ever reaches the open road, its story begins long before the first bolt is tightened or the first panel is painted. The creation of a Nissan car is a journey that blends advanced engineering, precision manufacturing, and human skill into a seamless, highly coordinated process. It begins in design studios and engineering departments, where the model is conceived, refined, and optimized for production. Design is never just about looks. For Nissan, every curve and contour is evaluated for aerodynamic efficiency, structural integrity, and manufacturability. Engineers work closely with manufacturing planners to ensure that the design can be built consistently at high volume. This process is called design for manufacturability, and it addresses questions like, can a panel be stamped without deforming? Can a wiring harness be installed without excessive labor time? Can a structural weld be made easily by a robot? These early decisions will determine the efficiency and quality of the factory floor operations months or even years later. Once the design is finalized, manufacturing engineering takes over. This is where the factory plan is built, specifying the sequence of operations, the type of machinery to be used, and the layout of the assembly line. Nissan's factories are often capable of building multiple models on the same line, which means the plan must account for mixed model production. In practice, this requires flexible tooling, quick change robotic programs, and precisely timed deliveries of parts so that the right components are always at the right station when a specific model arrives. The physical process starts with the arrival of raw materials, primarily steel and aluminum. These materials, often in the form of giant coils weighing several tons, are delivered by rail or truck to the plant's stamping facility. Before a single press stroke is made, the coils are unrolled, flattened, and cut into blanks, flat sheets of the correct size for the parts to be made. These blanks are then fed into huge stamping presses capable of exerting thousands of tons of force. Each body panel, whether it's a door skin, roof panel, fender, or hood, is formed by passing through several stages of dies. The first die forms the rough shape, while subsequent dies refine the panel, adding curves, ridges, and precise dimensions. The dies themselves are precision-engineered steel blocks that must be perfectly aligned and maintained to avoid defects. Quality checks start here. Robotic measuring arms or laser scanners inspect the panels for dimensional accuracy and surface quality. Even minor ripples or distortions can cause problems later during assembly, so any out-of-spec panels are removed from the line and sent for recycling. From stamping, the panels are moved into the body shop, a large, highly automated hall where the panels are welded together to form what is known as the body in white. This is the skeletal shell of the car before painting and assembly. Large jigs and fixtures hold panels in the exact position while robotic arms perform spot welds, fusing the metal together. In modern Nissan plants, robots handle the majority of welds, ensuring speed, repeatability, and strength. The process usually starts with the floor pan. Side panels, roof structures, and cross members are added in a carefully planned sequence to maximize rigidity and precision. Reinforcements for crash safety, such as high-strength steel beams in the doors and roof pillars, are installed at this stage. Doors may be temporarily hung for alignment checks, but are often removed later to make interior assembly easier. Although automation dominates, human workers remain essential. Some welds, especially in tight or complex areas, are better handled by skilled technicians. Workers also monitor the robotic systems, making adjustments when necessary and performing visual checks for weld integrity. When the body shell is complete, it undergoes a dimensional inspection using coordinate measuring machines or laser scanning systems. This ensures that the structure matches the precise dimensions required for later assembly steps, where mismatches can cause issues with panel fit or sealing. Next, the bare metal body heads to the paint shop, an area of the factory with the most stringent cleanliness requirements. Dust, dirt, and moisture can ruin a finish, so the paint shop is a sealed, climate-controlled environment. Before painting, the body goes through a series of pre-treatment baths to remove any residual oil or dirt from stamping and welding. These baths also apply a phosphate layer that improves corrosion resistance. After pre-treatment, the body undergoes electrophoretic deposition, or e-coating. In this process, the body is submerged in a primer bath where an electric charge causes the primer particles to bond evenly to the entire surface, including hidden cavities and seams. The coated body is then baked in an oven to cure the primer into a hard, protective layer. Once cured, the body is sanded to smooth the surface before the color coats are applied. Robotic sprayers, precisely programmed for each model and color, apply the base coat evenly over every contour. In some cases, human painters handle special finishes or complex two-tone applications. After the base coat, a clear coat is applied to provide gloss and protect against UV and environmental damage. Each coat is cured in an oven, hardening the finish and locking in the color. When the painted body emerges, it looks complete on the outside, but remains an empty shell. The next stage, trim and chassis assembly, is where the car starts to take shape as a functional vehicle. The first step in trim is installing sound deadening materials, insulation, and wiring harnesses. These harnesses, pre-assembled into model-specific layouts, are routed through the body and secured in place. HVAC ducting is fitted, followed by the dashboard, which usually arrives as a fully assembled unit from a supplier. seats are bolted into place, carpet is laid, and door panels are installed. In parallel, the plant's chassis line is assembling the mechanical heart of the car. The engine, transmission, suspension assemblies, exhaust system, and brakes are mounted onto a subframe or separate underbody unit. This modular approach allows for rapid final assembly once the chassis and body are ready to be joined. The marriage process is one of the most striking moments in Nissan's assembly line. The painted body is suspended above the rolling chassis module, and the two are brought together by synchronized lifts. Bolts are torqued to specification, connecting the drivetrain and suspension to the body. Following the marriage, technicians connect the various systems between body and chassis, electrical plugs, coolant hoses, fuel lines, steering linkages, and more. Windows are installed using high-strength adhesive, and exterior trim pieces such as weather strips, moldings, and badges are applied. At this point, the Nissan is a complete vehicle in form, but must still prove itself in function. The next phase, testing, inspection, and final adjustments, will determine whether it is ready for shipment to customers. With the major assembly work finished and the Nissan now standing as a complete vehicle, the factory's focus shifts toward verification, fine-tuning, and preparing it for the journey beyond the plant gates. This stage is not simply a final glance over the product, it is a comprehensive series of tests and inspections designed to ensure that every function operates exactly as intended and that the vehicle meets Nissan's rigorous quality standards as well as the legal requirements of its destination market. The first stop in this phase is usually the wheel alignment station. Here, precision laser or camera-based measurement systems determine the exact angles of each wheel relative to the chassis. Technicians adjust camber, caster, and toe to within factory specifications. A misalignment at this stage would not only affect handling and tire life, but could also cause warranty claims, so the process is handled with meticulous care. From there, the vehicle moves to the fluid fill and pressurization stage. While some fluids such as oil and coolant may have been partially filled earlier, this step ensures that all systems are fully charged to their specified capacities. Brake and clutch hydraulics are bled to remove any trapped air, guaranteeing a firm pedal feel. Air conditioning systems are charged with refrigerant, the fuel system is primed, and in hybrid or electric models, high voltage battery systems are energized and checked for correct operation. Each fill station uses automated metering systems to deliver exact volumes, minimizing waste and ensuring repeatability. One of the most anticipated moments comes next, the first engine start. At a dedicated station, the technician engages the ignition or push button start, bringing the Nissan's powertrain to life for the very first time. While this might appear ceremonial, it is primarily a diagnostic event. The vehicle's onboard computer is scanned for any fault codes, idle speed is observed, and technicians listen closely for any unusual noises or vibrations. If a warning light appears or a diagnostic scan reveals an error, the vehicle is diverted to a repair bay before continuing. Once the initial startup checks are complete, the Nissan moves to the rolling road, also called the chassis dynamometer. Here, the drive wheels rest on large rollers that simulate road resistance. A trained operator runs the vehicle through various speeds, load conditions, and gear changes, while onboard sensors and external instruments record performance. This stage verifies smooth transmission shifts, proper acceleration response, correct ABS function, and stability control operation. For electric and hybrid models, regenerative braking efficiency is also tested. Following the dynamic test, the vehicle enters the emissions and noise measurement booth. Exhaust gases are captured and analyzed to ensure compliance with the emissions regulations of the market the car is destined for, whether that's Europe, North America, or Asia. The booth may also include sound level monitoring to verify that engine and exhaust noise remain within acceptable limits. For some models, interior noise levels are also measured to maintain Nissan's comfort standards. With the drivetrain and emissions verified, the Nissan proceeds to the fit and finish inspection zone. This is a brightly lit area where experienced inspectors examine every exterior panel and interior surface. Panel gaps are measured to ensure uniformity, and paint is checked under angled lighting that reveals imperfections invisible in normal conditions. Inside, every control, switch, and display is operated to confirm proper function. HVAC systems are tested for both heating and cooling performance, infotainment units are powered on, and tested for audio quality, and safety features, such as seatbelt warning systems, are checked. One of the most critical functional tests is the water leak check. The car is driven into a sealed chamber fitted with high-pressure water nozzles that bombard it from all directions, simulating heavy rain or car wash conditions. After several minutes of soaking, technicians enter the vehicle to check for even the slightest signs of moisture. Any leak detected, whether from a window seal, door gasket, or body seam, results in immediate repair and retesting. Next comes the underbody inspection. The vehicle is lifted on a hoist so workers can examine fuel lines, brake hoses, exhaust components, and electrical wiring for correct routing and secure fastening. Protective coatings applied earlier in the build are checked to ensure they fully cover vulnerable areas, especially in regions prone to corrosion. This step also allows for one last visual confirmation that no tools, fasteners, or foreign objects have been left behind during assembly. The last in-plant checkpoint is the final audit. This is a comprehensive, multi-point inspection that serves as the ultimate quality gate before the vehicle is released for shipping. The audit team includes some of the most experienced inspectors in the plant, and their role is to verify that every system operates flawlessly. The process includes both static checks, such as lights, controls, and displays, and short, low-speed driving within the factory grounds to confirm steering feel, brake performance, and noise levels. When a Nissan passes the final audit, it is cleared for shipment. In the shipping preparation area, protective films are applied to painted surfaces most likely to be scuffed during transport, such as the hood, roof, and door edges. Interior surfaces like the seats, steering wheel, and carpets are wrapped with disposable covers. The cars are then driven to the factory's dispatch yard, where they are parked in organized rows according to their destination. Each vehicle is scanned into Nissan's logistics system using its unique vehicle identification number, linking it to production data, quality records, and shipping instructions. Domestic-bound cars are usually loaded onto multi-level car carrier trucks, with each vehicle secured using wheel straps or chocks to prevent movement. For longer inland journeys, rail transport in enclosed auto racks is sometimes used. Export vehicles are driven onto roll-on/roll-off ships, enormous vessels designed specifically for transporting thousands of cars at once. Inside the ship, the vehicles are parked in tight formation and secured with lashings to keep them stable during ocean crossings. When the ship reaches its destination port, Nissan vehicles are driven off and placed into secure holding areas for customs clearance. Once cleared, they are transported to regional distribution centers. Here, a process called pre-delivery inspection, or PDI, is carried out. Technicians remove transport protections, recheck fluids and tire pressures, confirm there is no transport-related damage, and make any market-specific adjustments, such as software updates or headlight aim changes. Finally, the vehicles are dispatched to dealerships, where a last brief inspection is done before placing them on the showroom floor or preparing them for immediate delivery to customers. The moment a buyer takes the keys marks the end of the manufacturing journey, but for Nissan, the process is part of a continuous loop. Feedback from customers and dealerships feeds back to engineering and manufacturing teams, influencing improvements for future models. The highlight of this stage is the marriage, when the body is lowered onto the chassis assembly. Using synchronized lifts, the two halves are brought together, and fasteners are torqued to precise specifications. At this point, the Chevrolet vehicle has its structural and mechanical systems fully united. From here, connections are made between the body and chassis systems. Electrical hookups, fluid lines, control linkages, and exhaust mounts are all secured. Windows are bonded into place with high-strength adhesives, exterior trim and badging are applied, and final adjustments are made to doors, hoods, and trunk lids to ensure perfect fit and operation. To understand how a Toyota car is made, one must first step into a space where discipline, precision, and respect for process define every movement, the Toyota factory. Within these facilities, the transformation from raw materials to a fully functional vehicle is not simply a mechanical progression, but a living manifestation of a philosophy. This philosophy, known globally as the Toyota Production System, or TPS, is centered on two foundational pillars: Jidoka, automation with a human touch, and just-in-time manufacturing. Together, these principles dictate how every Toyota vehicle is born. Imagine walking into one of Toyota's flagship plants, such as the Tsutsumi plant in Toyota City, Japan, or the Georgetown facility in Kentucky. The air is filled not with chaos, but with a quiet, rhythmic hum. It is not the sound of urgency, but of synchronization. Workers, robots, and machines operate in precise harmony, each step of the process unfolding like clockwork. Every bolt tightened, every part aligned, every inspection performed. Nothing is rushed, but nothing is delayed. The objective is not to build fast, but to build flawlessly, and in the smallest increment of time and resource necessary. The beginning of any Toyota vehicle starts far upstream, not in the plant itself, but in the raw material supply chain. Toyota sources high-strength steel, aluminum, plastics, semiconductors, glass, and countless other materials through a tightly managed supplier network. Each supplier is held to stringent quality and delivery standards. Deliveries arrive at the plant just in time, often within hours of their use. This lean inventory philosophy reduces waste and ensures that the factory remains agile, able to adapt to shifting demands or changes in vehicle variants without maintaining massive backstocks. Once materials arrive, the first physical steps in vehicle creation occur in the stamping shop. Here, massive coils of steel or aluminum are loaded into enormous stamping presses, machines that weigh hundreds of tons and exert enough force to shape thick metal in a single, clean motion. These presses are fitted with die sets, precision-engineered molds that stamp out individual body components like fenders, hoods, roofs, and doors. The dies are swapped out by automated systems within minutes, allowing the line to shift seamlessly between models with minimal downtime, a critical capability in a mixed model facility. The stamped panels are then transported, often via overhead conveyor systems or autonomous carts, to the welding shop, the domain of the body in white. Here, the core structure of the car takes shape. Robotic arms, fitted with weld guns and sensors, orchestrate a ballet of sparks. These machines are programmed with exacting specifications to apply spot welds at predefined intervals, securing body panels together into a rigid, cohesive structure. Human technicians oversee the process, performing inspections, handling complex geometries, and activating andon systems, alert cords, should any defect be found. Toyota's concept of Jidoka is exemplified here. Each welding station is empowered to halt the entire line if a defect or misalignment is discovered. This is not seen as failure, but as a safeguard for quality. Rather than allow a potentially flawed product to progress, the issue is stopped at its source, analyzed, and resolved before production resumes. Workers are trained not just to follow instructions, but to improve the process. This continuous improvement culture, known as Kaizen, is deeply embedded in every team member, from entry-level assemblers to plant managers. Once the car body has been assembled and verified for dimensional accuracy using laser measuring systems, it proceeds to the paint shop, where it is cleaned, sealed, primed, and finally painted. Before any color is applied, the body is immersed in a series of baths for electrodeposition coating, a process that prevents corrosion by electrically bonding a primer to the metal surface. The body then moves through a drying oven before entering the color application booths. Inside the paint booths, robotic arms fitted with rotary atomizers apply successive layers of primer, base coat, and clear coat. Each coat is inspected under intense lighting and humidity-controlled conditions to ensure consistency and to prevent inclusions such as dust or overspray. Technicians perform visual inspections and touch tests, sometimes sanding and reapplying paint if surface imperfections are found. The body then enters a final curing oven, where it is baked at high temperatures to harden the paint finish. By now, the car's basic structure is complete and coated, but it still lacks its soul: the engine, drivetrain, electronics, and interior. These elements come together in the general assembly area, a zone that stretches across hundreds of meters and involves hundreds of interwoven processes. It is here that Toyota's just-in-time philosophy truly comes alive. Unlike traditional batch manufacturing, Toyota's production line is mixed model, meaning different car types and trims, even with different engines or drive systems, are produced on the same line in whatever sequence is dictated by real-time customer orders. To accommodate this, parts are delivered in sequence to the line. If the next car is a Corolla hybrid with a panoramic roof, the exact seat configuration, roof headliner, battery pack, and other components for that configuration arrive seconds before the car reaches the station where they'll be installed. One of the most critical events in the assembly process is known as the marriage, the point at which the painted body is lowered onto the pre-assembled chassis. The chassis includes the engine, transmission, suspension components, exhaust system, and drivetrain. These assemblies are built up in parallel lines and synchronized with the main body line so that both components arrive at the marriage station at precisely the same moment. As the body descends onto the chassis, guided by precision jigs and hydraulic lifts, technicians align mounting points and fasten critical bolts using torque-controlled tools. Every fastening operation is digitally logged and monitored. If a bolt is under or over-torqued, or if a tool slips, the system immediately alerts the operator. These digital confirmations ensure traceability and enable Toyota to maintain records for every car that leaves the factory, supporting future warranty claims, recalls, or quality assurance audits. After marriage, the car begins to take on its recognizable interior form. Dashboards are installed as single pre-assembled units, often produced by Tier 1 suppliers in nearby satellite facilities and delivered just in sequence. Seats, wiring harnesses, air conditioning modules, infotainment systems, and airbags are carefully installed in a series of tightly choreographed steps. Workers use a combination of hand tools, smart torque guns, and pick-to-light systems, which light up the exact part bins for each operation to ensure accuracy and speed. This process continues with the installation of glazing, lighting elements, bumpers, wheels, and various trim components. Every part is fitted under strict quality standards with gap alignment and surface flushness, checked visually and digitally using laser systems. During each step, workers remain empowered to pull the and-on cord if they detect an anomaly, reinforcing Toyota's belief that quality is built in, not inspected in. Once the assembly is complete, the vehicle is no longer a shell or a skeleton. It is a living machine, but one that has not yet been proven. The next phase will test every system, calibrate every sensor, and ensure that the Toyota badge on the front carries with it the weight of reliability, safety, and trust. Following the completion of physical assembly, each Toyota vehicle enters one of the most critical phases of the production lifecycle: the inspection, calibration, and functional testing stage. This is where mechanical craftsmanship meets analytical scrutiny. Every car must now prove that it not only fits together correctly, but that every system operates as designed, with the precision and reliability Toyota is globally known for. The first area the vehicle enters is typically the initial quality gate. Here, a multi-point check is performed by trained inspectors who methodically examine structural components, body alignment, and basic mechanical fitment. Every door, trunk, and hood is opened and closed to assess alignment and sound. Uneven gaps, misaligned panels, or abnormal resistance are noted and corrected on the spot. Workers use gap gauges, flushness sensors, and manual inspection tools to detect even the smallest deviations in build quality. From there, the vehicle proceeds to dynamic system checks. This is where the car begins to come to life, electronically and mechanically. A technician connects the vehicle to a factory diagnostic system, uploading the final software package to all electronic control units. In a modern Toyota, there can be 30 to 80 ECUs depending on the model, each managing a different subsystem, such as braking, power steering, stability control, hybrid drive, airbag systems, and infotainment. The ECUs are flashed with firmware specific to the car's trim level, engine type, and market destination. This step is highly sensitive, with redundant data verification systems to ensure the software uploads completely and correctly. Once configured, the system initiates a global self-check, where the vehicle essentially performs a diagnostic scan of itself. Each ECU confirms its functionality and readiness, while the technician monitors for error codes or inconsistent behavior. Any anomaly is logged and triggers a deviation procedure where the vehicle may be diverted to a separate diagnostics bay for deeper troubleshooting. Next, the car is transferred to a specialized station for fluid filling and pressure testing. Here, automated systems dispense exact volumes of engine oil, brake fluid, coolant, washer fluid, and, for hybrid or electric models, inverter coolant or battery thermal management fluids. These filling stations are digitally calibrated to prevent overfilling or contamination. During this stage, systems are also pressurized and sealed, then tested for leaks using pressure sensors and flow meters. Brake lines are tested by pressurizing the system and monitoring for pressure drops, ensuring every car leaves with a perfect, air-free hydraulic system. At this point, the vehicle is ready for its first engine start. A technician initiates ignition using either a key fob or the factory diagnostic console. The vehicle turns over and the engine comes to life. During this brief but critical startup phase, the system monitors RPM, oil pressure, exhaust sensor feedback, charging voltage, and other vitals. The technician listens for abnormal engine noise, checks idle quality, and watches for leaks or warning indicators. Once the engine stabilizes, the vehicle begins a series of automated or semi-automated functional tests, including shifting through gears, verifying steering assist, and checking basic throttle response. With the engine running and fluid circulating, the vehicle now moves to the dynamic test track or rolling road, depending on the facility's layout. On a rolling road, a stationary test bench with rotating drums. The car is accelerated through a simulated driving sequence. Braking, acceleration, shifting, emissions control, and hybrid transitions are all tested under load. This is where software calibration is fine-tuned. For example, hybrid systems may be evaluated for smooth transitions between electric and gasoline power, while adaptive cruise control sensors are calibrated to recognize distance targets. Meanwhile, headlight aim is adjusted using laser-guided alignment equipment. Wheel speed sensors are tested, and the vehicle's onboard safety systems, such as ABS and traction control, are confirmed to respond appropriately to artificial inputs. On some high-spec models, even the sound insulation is checked using internal microphones while simulating wind and road noise inside a soundproof chamber. Following dynamic testing, the car is driven to a water test booth, an enclosed chamber equipped with high-pressure nozzles, positioned to simulate heavy rain, splash conditions, and high-speed water exposure. The entire vehicle is blasted with water from above, below, and the sides. Technicians inside the booth or using moisture detection tools afterward check the interior for any signs of leakage, particularly around doors, glass seals, sunroofs, and underbody grommets. Vehicles that fail this test are sent to a specialized sealing team for inspection and repair before re-entering the final inspection queue. The penultimate step in the process is the final visual and tactile inspection line, often referred to as the white light tunnel. In this area, powerful overhead lights and side lighting replicate broad daylight, revealing surface imperfections invisible under factory lighting. Inspectors move around each vehicle slowly, checking for micro scratches, paint defects, misaligned trim, dirt under the clear coat, and material inconsistencies. The tactile elements are just as important: seat firmness, stitching alignment, trim tightness, and even the smoothness of control knob rotation are checked against factory benchmarks. Finally, once all systems are verified, paint and finish are pristine, and data records confirm the vehicle's complete build and performance history, the car is released from production. A digital certificate is issued, containing every measurement, torque value, fluid fill, software version, and test result from each phase of assembly. This data is stored in Toyota's secure manufacturing archive and is linked to the vehicle's VIN for life. If a component recall, software update, or warranty claim ever arises, this record becomes the reference point for diagnostic and corrective action. As a last step, protective films are applied to vulnerable surfaces like the hood, doors, and bumpers to prevent damage during transport. The vehicle is then driven to the shipping yard where it is scanned, parked, and queued for delivery via truck, rail, or ship, depending on its final destination. The birth of a Honda automobile is not an accidental fusion of metal, glass, rubber, and electronics. It is the physical realization of a manufacturing philosophy rooted in discipline, simplicity, and human respect. At the core of Honda's automotive production process is the concept of monozukuri, a Japanese term meaning making things with craftsmanship and pride. For Honda, monozukuri is not just about building cars. It's about building trust in every nut and bolt, in every weld seam, in every panel gap. To witness a Honda car being built is to enter a tightly orchestrated environment where technological sophistication meets manual precision. Inside one of Honda's production facilities, such as the plant in Marysville, Ohio, or the Sayama factory in Japan, the scale is staggering. These plants are sprawling ecosystems of autonomous vehicles, robotic cells, and human operators working side by side across multiple production halls. And yet, despite their size and complexity, the rhythm of the process remains surprisingly calm. Everything flows according to plan, governed by Honda's unique lean manufacturing philosophy known as the Honda Production System. The journey of a Honda car begins long before any metal is cut. It starts with production planning, a phase driven by market forecasts, dealer input, supply chain readiness, and model demand. Honda's plants operate on a build-to-order basis more than most automakers. That means production schedules are crafted based on actual customer orders and real-time market demand. This approach minimizes inventory waste and maximizes the efficiency of the supply chain. Once the schedule is locked in, suppliers across the globe begin preparing the thousands of components that will soon converge at the plant. Raw materials like steel and aluminum arrive at the factory in massive coils. These materials first enter the stamping department, a cavernous space filled with towering hydraulic presses. Each press is fed with sheet metal and fitted with enormous dies, complex mold tools shaped to form specific vehicle panels, such as hoods, doors, roofs, and fenders. The dies are interchanged automatically using massive overhead cranes and quick change systems, allowing the factory to shift between different vehicle models with incredible speed. These presses apply thousands of tons of force in milliseconds, transforming flat sheet metal into high-precision components with reinforced curves and load-bearing geometries. Each stamped panel is checked using template gauges or laser measuring arms to verify its accuracy against design tolerances. Honda's emphasis on dimensional precision at this early stage ensures that all panels fit perfectly during final assembly, which in turn improves both structural integrity and noise insulation. The stamped panels next travel to the welding shop, where the vehicle's skeleton, known as the body in white, is assembled. This stage is a symphony of automation. Dozens of robotic arms arc and swivel across each cell, welding panels together with pinpoint accuracy. These arms are fitted with spot weld guns, seam welders, laser cutting tools, and even rivet actuators, all pre-programmed for the vehicle model and trim level currently on the line. Guided by 3D coordinates, these robots can perform hundreds of welds in just a few minutes. Despite this high degree of automation, human workers play a vital role. Technicians monitor robotic operations, inspect weld seams visually, and perform manual welding in areas where robots cannot easily reach, such as complex internal joints or tight cavities. Importantly, Honda applies its stop-the-line authority in this department. Any associate who detects an issue is empowered to halt the line and initiate corrective measures immediately. This is part of Honda's respect for humanity approach, trusting operators not just to follow instructions, but to contribute actively to product quality. Once the weld shop produces a complete body shell, it enters the sealing and corrosion protection area. At this stage, structural adhesives and sound dampening materials are applied to critical areas of the body, such as the floor pan, roof seams, and door frames. These materials increase rigidity, improve crash performance, and reduce road noise. Seams are also sealed with flexible gaskets to protect against water ingress. After sealing, the body is conveyed to the paint shop, one of the most technologically advanced sections of the plant. Before any color is applied, the car is submerged in a series of cleaning and surface preparation baths. These include alkaline washes, acid baths, and a crucial e-coating step, in which the entire body is dipped in an electrically charged primer solution. The electrical current causes corrosion-resistant particles in the bath to bond uniformly with the metal, even in hard-to-reach crevices and weld joints. Once the e-coat is cured in an oven, the body enters a clean room environment for the color painting process. Robotic arms with electrostatic spray guns apply the primer, base coat, and clear coat in successive layers. Each layer is air-dried or heat-cured to ensure optimal adhesion and durability. Honda's paint robots use feedback-controlled nozzles that adjust spray patterns dynamically based on body shape and angle, reducing overspray and minimizing environmental impact. Between layers, the vehicle is visually inspected under specialized lighting conditions. Technicians look for drips, dust contamination, and color uniformity. If any issues are found, the body is flagged for manual repair, which may include sanding, buffing, or repainting a specific panel. Once painting is complete and the final clear coat has cured, the body is ready for general assembly, the stage where it transforms from a painted shell into a fully functioning automobile. Before reaching the general assembly line, however, many key sub-assemblies are built in parallel feeder lines located throughout the plant. These include engine and transmission modules, suspension components, dashboards, interior trim sets, seat assemblies, and wiring harnesses. Honda practices a synchronized subassembly strategy. Each of these components is produced and sequenced in real time to meet the exact build order of the cars progressing down the main assembly line. That means if car number 287 is a Honda Accord hybrid in touring trim, every part of that specific configuration is queued and ready to install by the time the body reaches the relevant station. When the painted body reaches the main assembly line, it is mounted onto a moving conveyor system. This conveyor will carry the vehicle through dozens of stations, each performing a specific set of installations or tests. The first few stations focus on interior preparation. Sound deadening mats are applied to the floor. Wiring harnesses are routed through the firewall and chassis, and the dashboard is bolted into place. Honda uses pre-assembled dashboard modules, which include the instrument cluster, HVAC system, infotainment screen, and most switches, all pre-tested before installation. This reduces line complexity and improves consistency. Seats, carpeting, door panels, and airbags follow shortly after. At every step, workers use a system of digital instructions, torque control tools, and pick-to-light part bins to ensure that the right part is used and installed to the correct specification. Honda's goal is zero deviation from build order, even in mixed model lines, producing different trims every few minutes. As interior installation continues, the process becomes more intricate. With the dashboard now secured, the vehicle receives its electrical control units, sensors, and remaining interior electronics. These are connected to the pre-installed wiring harnesses using color-coded, click-locked connectors that help eliminate the possibility of human error. Specialized quality control stations may test critical modules immediately after connection, especially airbag sensors and crash detection systems, to ensure they are responsive and correctly integrated into the vehicle's network of ECUs. Following this, attention turns to glazing and weather sealing. Robots or trained technicians carefully install front and rear windshields, applying adhesive in a uniform bead to ensure a perfect seal. The installation is timed precisely as the adhesive cures rapidly. Door windows, quarter glass, and side mirrors are added next, with their mechanisms tested on the spot to ensure smooth operation. Throughout this process, jigs and fixtures are used to maintain tight tolerances between the panels and glass, ensuring aerodynamic integrity, road noise insulation, and weather protection. The vehicle then reaches one of the most pivotal points in the production process, the powertrain marriage. As the body travels down the assembly line, a pre-assembled drivetrain module consisting of the engine, transmission, front or all-wheel drive differential, and suspension subframe arrives underneath on a separate conveyor. The marriage station uses synchronized hoists and laser-guided platforms to lift the body and lower it gently onto the drivetrain assembly. Once aligned, operators bolt the body to the subframe using hydraulic torque tools, which log each torque application in real time for quality traceability. The process of mating the body to the chassis and powertrain is more than a mechanical operation. It's an integration of identity. From this moment, the car ceases to be a shell and becomes a functional vehicle. After the marriage, systems are connected. The fuel lines, brake lines, wiring looms for sensors and control modules. Axles are bolted in. Radiators and intercoolers, along with their coolant hoses, are fitted. Exhaust systems are clamped into place and routed along the underbody using guides to prevent rattle or contact with heat-sensitive zones. Next come brake systems and suspension components. Brake calipers and discs are attached at each corner, followed by routing and fastening of hydraulic lines. ABS sensors and wheel speed sensors are snapped into their mounts, and their cables are clipped securely to avoid movement. Meanwhile, shock absorbers, Coil springs or struts are fastened to the body using calibrated robotic arms or torque-controlled tools operated by line workers. These fasteners are critical as they influence ride quality, safety, and steering behavior. The wheels and tires, pre-mounted and balanced in a separate line, are then delivered just in time to the vehicle. They are aligned to the hub assemblies and fastened using pneumatically powered tools equipped with digital torque sensors. Each wheel torque is logged and checked against specifications. Even minor deviations trigger alerts. For instance, over-tightening a lug nut can damage threads or warp brake rotors, so precision is not optional. By this stage, the vehicle is mechanically complete, but not yet operational. It now passes into a startup and calibration zone, where the first true interaction between systems begins. Trained technicians perform a key-on sequence where all electronic systems are activated. This step includes powering up the main vehicle bus, initializing communication between ECUs, and performing a cold test of lighting systems, instrument clusters, wipers, and cabin electronics. The technician uses a diagnostic console to verify proper communication between modules and applies any last-minute software updates if required. Once the vehicle's systems are verified and error-free, the engine is started for the first time. A moment that is both mechanical and symbolic. As the engine cranks and catches, onboard diagnostics immediately monitor oil pressure, exhaust emissions, idle speed, coolant flow, and electrical charging. If any of these parameters fall outside of the calibrated range, the system flags the vehicle for further inspection. For hybrid models, the electric drive system may initiate instead, with the gasoline engine starting only after the battery's state of charge reaches a specific threshold. After the successful start, the car enters the rolling road test or chassis dynamometer. Here, it is strapped to large rollers that simulate road conditions. The car is driven through a standard cycle of acceleration, braking, shifting, and cruising, all while remaining stationary. This test evaluates key systems, including ABS, traction control, throttle response, gear engagement, hybrid transitions, and engine tuning. Sophisticated sensors and computers monitor hundreds of data points per second, ensuring the vehicle performs exactly as designed. Following the rolling test, the vehicle undergoes a headlight alignment and safety calibration station. Here, laser-guided systems measure the alignment of headlamps, and adjustments are made to meet both manufacturer and regional regulations. Advanced driver assistance systems such as lane keeping assist, adaptive cruise control, and forward collision warning are also calibrated at this point. This is accomplished using visual targets placed at known distances and angles in front of the vehicle, allowing cameras and radar units to learn their field of vision relative to the car's center line. Once these tests are complete, the vehicle proceeds to the water leak test booth, a sealed chamber equipped with an array of high-pressure water jets. For several minutes, water is sprayed at every angle, above, below, and from the sides, mimicking hurricane-force rain. Technicians inspect the cabin interior afterward for leaks, particularly around window seals, sunroofs, and door frames. Any sign of moisture sends the vehicle to a sealing team for immediate remediation and retesting. The car now moves into the final inspection area, often referred to as the white light tunnel. This zone is illuminated by intense, color-corrected lighting systems that reveal even the smallest defects in paint, fitment, and alignment. A team of inspectors walks around each vehicle, using mirrors to check lower panels, feelers to check panel gaps, and gauges to measure surface flushness. They assess the finish of paint, the gloss consistency, the evenness of door gaps, and the snugness of interior trim. Particular attention is paid to areas around weld joints, door hinges, and tailgate edges where minor misalignments can occur. Each inspector has the authority to flag the vehicle for any observed issue, no matter how small. Flagged cars are moved to a rework area where expert technicians resolve any concern before the vehicle can be released. Rework stations are not viewed negatively. They exist to ensure that every vehicle that exits the factory is indistinguishable from one that passed cleanly through all stages. After final inspection, the vehicle is prepared for delivery. Protective plastic sheeting is applied to painted surfaces and interior areas prone to contact during transport. The car is then driven to a shipping lot, where it is scanned into inventory and parked according to destination. Vehicles headed for domestic markets are grouped by dealership region and loaded onto transport carriers, while those bound for international markets are routed toward ports and loaded onto ships. The Honda factory's job may seem finished here, but in truth, its responsibility continues well beyond the factory gates. Each car's production data, including every torque value, software version, fluid fill level, and test result, is linked to its unique vehicle identification number and stored securely in Honda's manufacturing cloud. If an issue ever arises in the field, Honda can trace it back to the exact moment and operator involved in the car's creation. To witness the making of a Ford vehicle is to observe the evolution of industrial craftsmanship, a living embodiment of the assembly line system first pioneered by Henry Ford over a century ago, and refined today into a symphony of automation, digital intelligence, and human engineering. In modern Ford factories, like the Rouge Complex in Dearborn, Michigan, or the Oakville Assembly Plant in Ontario, production isn't simply about building cars. It's about orchestrating a precisely timed flow of materials, people, and machines that together transform raw components into advanced, drivable technology. The process begins long before the first bolt is turned or the first panel is stamped. The foundation of Ford's modern production system lies in rigorous planning and global coordination. Ford operates with a just-in-time and just-in-sequence supply chain strategy, meaning that materials and components arrive at the factory floor moments before they are needed. This eliminates the need for large stockpiles of inventory and increases the plant's flexibility to respond to changes in production schedules or model configurations. Planning starts with demand forecasting and order management. Using a centralized production planning system, Ford determines what models, trims, colors, and drivetrain variants will be built on any given day based on global dealer orders, regional demand patterns, and parts availability. This build mix is then converted into a master schedule that guides every action in the plant, from how robots are programmed, to which parts are loaded into which bins on which carts. At the heart of every Ford plant lies the stamping facility, where large rolls of sheet metal, primarily steel and aluminum, are cut and formed into individual body panels. These sheets arrive from external suppliers and are checked for thickness, flatness, and coating quality before entering the production line. Inside the stamping area, massive hydraulic or mechanical presses, sometimes up to 30 feet tall, use high tonnage force to shape the sheets into components such as hoods, roof panels, fenders, doors, and floor pans. Each stamping press contains tool and die sets, which are the sculpted steel molds that give shape to the metal. Changing these dies can take several hours on older systems, but Ford's modern plants use quick change tooling and automated die swapping cranes, allowing multiple model variants to be stamped in a single shift. Once stamped, each panel is inspected using automated vision systems and tactile measuring tools to ensure dimensional accuracy and surface quality. These stamped parts are then sent via conveyor or robotic shuttle to the next critical phase: body construction. In the body shop, robots dominate the floor. Here, the car's skeletal structure, called the body in white, is assembled from stamped panels. Using a combination of spot welding, MIG welding, and adhesive bonding, robots join together hundreds of individual panels to form a rigid structure that meets crash and durability standards. Each robotic cell is carefully synchronized, with arms moving in mirrored patterns to weld seams, attach reinforcements, and secure structural elements like the rocker panels and cross members. The entire body structure is periodically scanned with laser measurement systems. These 3D scanners create digital models of the assembled body to verify that it remains within tight tolerances. Even the smallest variation, fractions of a millimeter, could cause issues with later stages, such as door alignment or windshield fitting. If a body is found out of spec, it is automatically flagged and removed from the line for correction or further inspection. While the robots do the bulk of welding, human operators in the body shop play crucial roles. Some welds require access to tight spaces that robots can't easily reach. In addition, skilled technicians perform tactile inspections, feeling for uneven surfaces, sharp edges, or anomalies that a vision system might miss. They are also empowered to stop the line using an and-on system, a visible alert mechanism that signals an issue requiring immediate attention, a practice inherited from lean manufacturing disciplines. Once the body is complete, it's sent to the paint shop, a sealed and environmentally controlled environment that is perhaps the most intricate and sensitive area of the plant. But before paint can be applied, the body must be cleaned, prepped, and protected. It first enters an electrodeposition tank, or e-coat bath, where it is submerged in a liquid anti-corrosion primer. An electric current causes this primer to bond uniformly to every surface of the body, inside and out, including hidden cavities where rust could otherwise form over time. After curing in an oven, the body moves into a multi-stage painting process. Robots apply layers of primer, color, and clear coat using electrostatic spray guns, which attract paint particles to the metal surface like a magnet. The advantage of this method is increased efficiency and reduced overspray, leading to lower paint consumption and a cleaner environment. Ford's paint booths are equipped with air filtration and humidity control systems to eliminate dust or contaminants that could mar the finish. At each stage, lighting conditions are precisely calibrated to reveal imperfections, and technicians are stationed throughout the booth to perform quality checks. If a blemish is detected, a run in the paint, an uneven finish, or a missed spot, the vehicle is diverted to a paint repair zone where the affected area is wet sanded, resprayed, or polished by hand to meet Ford's appearance standards. After the final coat, the body undergoes a final curing process in a high-temperature oven to harden the paint and create a durable, glossy finish. The now fully painted vehicle shell, known as the trimmed body, advances to the general assembly line. This is the most labor-intensive section of the factory, where machines and humans collaborate closely. Unlike the body shop, where robots dominate, the general assembly area relies more heavily on human hands, precision tools, and ergonomic aids. The car body is mounted on a moving conveyor system known as a skillet line or friction drive platform, which carries the car through a series of workstations at a constant, carefully controlled speed. Assembly begins from the inside out. First, teams install insulation pads and sound deadening materials. Next, wiring harnesses, which form the car's electrical nervous system, are laid out and clipped into position along the floor, firewall, and side panels. Each harness contains dozens of connectors that will link to ECUs, lighting elements, climate controls, sensors, and powertrain systems. Proper routing and fastening of these cables are essential for both performance and safety, so visual checks and scanner-based validations are used at multiple points. Then comes the dashboard module, which is typically pre-assembled in a nearby subline. It includes the steering column, HVAC ducts, infotainment screen, and instrument cluster. This large component is inserted into the cabin as a unit using mechanical arms and then bolted into place. Seats, carpeting, interior trim panels, seatbelt retractors, airbags, and roof liners follow, each added in a precise order, with visual and tactile inspections performed continuously to ensure flawless fit and finish. Throughout this interior build process, Ford uses error-proofing tools such as torque-controlled wrenches, pick-to-light bins, and vision-guided assist arms. Every torque application is digitally logged. If a bolt is over or under-torqued, the system automatically halts the line and flags the issue. This traceability is vital, not only for quality assurance, but also for future diagnostics should the vehicle need service or become subject to a recall. Continuing from the general assembly line, the next transformative step in the creation of a Ford vehicle is the marriage of the painted body with the powertrain and chassis systems, a defining moment in every car's life on the line. As the body shell makes its way along the conveyor, the fully assembled engine, transmission, suspension, and front subframe approach from a lower parallel track. These components, built and tested in a separate sub-assembly area, are synchronized to arrive at the exact moment when the body reaches the marriage station. Here, specialized lifting systems raise the powertrain module from below while the body is gently lowered from above. Technicians, supported by robotic arms and torque-controlled tools, fasten the body to the chassis at critical mounting points. This precise alignment is essential. It determines the geometry of the suspension, the drivetrain angles, and even the behavior of noise and vibration through the cabin. Fuel lines, coolant hoses, drive shafts, brake lines, and wiring harnesses are then connected between body and chassis, integrating the mechanical and electrical systems into a unified vehicle. After the marriage, the vehicle receives its cooling system, air intake, and exhaust components, followed by fluids, including engine oil, brake fluid, transmission fluid, and coolant, all filled using automated dispensers that monitor volume, pressure, and flow rate. These filling stations ensure consistency down to the milliliter, and if there is any deviation from the programmed values, the system stops the process and flags the vehicle for investigation. With the engine installed and fluids topped off, the vehicle is now nearly complete. It receives its wheels and tires, which are pre-mounted, balanced, and matched to the specific trim and model variant. These are installed using torque monitoring impact wrenches, and the system logs each wheel's torque values in the vehicle's digital build record. Exterior components such as bumpers, lights, badges, grille assemblies, and mirrors are now added, bringing the vehicle's final form into view. At this stage, the car has all its physical components, but it still needs to come to life. The next section of the line is dedicated to initial startup and systems calibration. A technician connects the vehicle to a diagnostic console and performs the first ignition sequence. This process powers up the ECUs, activates safety systems, and starts the engine. Immediately, a flood of data is captured: oil pressure, engine RPM, voltage, emissions readiness, and more. The technician watches for warning lights, verifies software synchronization, and confirms that all onboard systems are responsive. If all readings are within specification, the vehicle advances to functional testing, where every major system, lights, brakes, steering, wipers, infotainment, HVAC, and electronic safety aids, is tested in a rapid, choreographed routine. Ford technicians use handheld devices and sensor panels to trigger functions and confirm their proper operation, all while the vehicle moves slowly along the inspection path. Any anomaly here diverts the vehicle to a diagnostics bay for further analysis. The story of an H2R does not begin on the assembly line. It begins much earlier, within the metallurgical divisions and materials labs that prepare the raw constituents of the motorcycle's essential components. At this initial stage, the journey starts with a block of high-tensile steel alloy specifically formulated for the H2R's trellis frame. This isn't ordinary steel. Kawasaki engineers designed the alloy composition to maximize tensile strength while balancing torsional rigidity and ductility. Sheets and tubing are delivered to the fabrication facility in precisely measured cuts, each one traced through an internal lot tracking system for complete traceability. Within the factory, the raw frame tubing undergoes cold drawing, a process that pulls the steel through dies to fine-tune its dimensions and surface integrity. Cold drawing is chosen specifically because it preserves mechanical strength while yielding tight dimensional tolerances, which are critical for the trellis frame's intricate geometric structure. Robotic armatures position each steel tube beneath automated laser cutting heads that slice the tubes into exact segments, using CNC-defined angles to ensure proper later fitment during welding. The accuracy here is staggering. Deviations beyond 0.1 millimeters trigger alerts in the system, halting the production cell for inspection. These cut tubes are then transferred via automated conveyors to a robotic frame welding station. Unlike mass-market motorcycle frames, the H2R's frame is entirely hand-welded, albeit with robotic support for fixturing and alignment. Skilled technicians, each trained for months on frame-specific geometries, perform manual TIG welding to fuse the chromoly steel components together. This welding process isn't just about joining metal. It's a delicate operation, balancing thermal input and cooling rates to avoid internal stress or warping, which could compromise high-speed stability at over 300 kilometers per hour. Once the frame is assembled, it enters a dimensional verification stage utilizing 3D laser scanning. The scanning head, mounted on a 6-axis robotic gantry, creates a digital twin of the physical frame, comparing it to the original CAD model within fractions of a millimeter. If the frame passes all checks, it moves to a powder coating line where it is electrostatically coated and oven cured at controlled temperatures. The specific gloss and hardness of the black frame coating are chosen for both heat resistance and resistance to rock chips and vibration-induced wear. Meanwhile, in another section of the plant, the supercharged engine, the beating heart of the H2R, begins its life in the engine assembly hall. This hall is a restricted environment, temperature and humidity controlled, and acoustically insulated from the rest of the plant. The reason is simple. The inline 4-cylinder engine that powers the H2R is not just another power plant. It's an ultra-high performance 998cc unit, force-fed by a centrifugal supercharger capable of spinning at up to 130,000 RPM. Such precision demands a sterile, meticulously maintained production environment. Engine block castings arrive from Kawasaki's dedicated foundry, having been machined to spec using 5-axis CNC centers. These blocks are inspected using ultrasonic resonance techniques to detect subsurface anomalies that cannot be seen visually or through surface scanning. If the casting passes inspection, it is mounted onto an engine cradle fixture, and the first stage of assembly begins. The installation of crankshaft bearings. Each bearing shell is hand micrometered and color-coded marks are applied to designate their oil clearance class. This step is crucial because the H2R engine tolerances are far tighter than in commuter bikes. The goal is minimal oil film thickness for maximum responsiveness without inducing friction-related failures. After the bearings are installed, the forged steel crankshaft is delicately lowered into the block. This crankshaft, balanced to aerospace-grade tolerances, is laser etched with its unique serial number for tracking and quality assurance. Next, titanium connecting rods and forged pistons are assembled offline on dedicated piston rod mating benches. Each piston is weighed and matched to its rod to within 0.5 grams to ensure uniform reciprocating mass balance. Piston rings are installed using rotary ring expanders that ensure even pressure and no deformation. The piston assemblies are then inserted into the engine block using hydraulic-assisted ring compressors, and the crankshaft is rotated by hand through a flywheel fixture to ensure smooth, unimpeded movement. Even the tiniest resistance would be flagged as an indicator of misalignment or contamination. Once the bottom end is secured and torqued in a cross pattern using digitally calibrated torque wrenches, attention shifts to the cylinder head. The H2R cylinder head is a complex component, machined with pent roof combustion chambers, large titanium valves, and dual overhead camshafts. Valve springs are installed using a pneumatic valve spring compressor, and valve lash is adjusted using precision shims measured to within hundredths of a millimeter. Camshafts, hardened and micro-polished, are mounted on journal caps and rotated to align with timing marks on the crank. The timing chain, a double roller unit, is fed through a guide channel and connected to the crank sprocket, then tensioned using a hydraulic chain tensioner preloaded with assembly oil. Once aligned, the engine is rotated again by hand, and valve timing is confirmed using a laser cam phase analyzer that calculates exact intake and exhaust overlap degrees. Now comes the installation of the supercharger, the defining feature of the H2R. The supercharger is assembled in a separate clean cell. Its impeller, machined from a single billet of aluminum, is balanced using high-speed spin balancers before being mounted to the planetary gear drive. The planetary gear unit, in turn, is gear-driven from the crankshaft and is fitted with helical-cut gears to reduce noise and increase torque handling. Once mated, the entire supercharger is tested in a closed-loop bench system, where it is spun up using a drive motor to simulate load and airflow output. Only if it meets the volumetric efficiency thresholds is it approved for installation onto the engine. As the supercharger is bolted onto the engine using a dedicated torque fixture, the entire power plant assembly is now ready to move to the dyno test cell. But before that happens, it's moved to a pre-test station where all fluids are filled. High-temperature synthetic oil, long-life coolant, and a special break-in fuel blend optimized for seating piston rings under load. The engine is then mounted into a test cradle wired with sensors and bolted to an eddy current dynamometer. Here, engineers run the engine through a programmed break-in cycle, gradually increasing load and RPM while monitoring combustion pressure, knock, oil pressure, and temperatures. Each engine must meet specific power output metrics before it's allowed to leave the test cell. For the H2R, this figure is over 310 horsepower measured at the crankshaft. Engines falling short are automatically rejected and moved to a forensic diagnostics bench where engineers determine whether the issue lies in fuel delivery, boost pressure, valve timing, or internal mechanical components. Once the dyno-tested engine has passed all performance and durability checks, it is removed from the test cradle and placed onto a specially designed rolling engine dolly. This dolly is more than a simple transport mechanism. It interfaces with hydraulic lift systems, allowing technicians to tilt, raise, and lower the engine precisely for the upcoming frame integration process. Before reaching the frame marriage station, however, the engine is routed through a pre-integration checkpoint where a technician conducts a final surface inspection, verifying all sealing surfaces, torque marks, and component connections. At this stage, all auxiliary components, such as the alternator, starter motor, oil cooler, and coolant hoses, are pre-mounted to reduce complexity during frame insertion. Meanwhile, the painted and fully inspected trellis frame, already cured and cooled from its powder coating process, is mounted on an assembly jig at the chassis preparation station. Here, the steering head bearings are greased and installed using an automated bearing press that ensures equal pressure distribution to avoid warping or damage. Into this steering head, the forged aluminum triple clamps are inserted and torqued to specification using a digital torque wrench with data logging capability. The handlebar mounts are temporarily attached for alignment purposes, but the handlebars themselves will come later in the line. At the engine marriage station, the prepped engine and trellis frame are brought together. A hydraulic lift slowly raises the engine into position beneath the frame, while two alignment pins guide the engine mounting points into perfect register with the frame brackets. 4 titanium bolts, lighter and stronger than traditional steel, are inserted and torqued in a diagonal sequence to avoid any stress concentrations. This step marks the true structural birth of the motorcycle. From this point onward, the machine is no longer a collection of parts. It is a unified mechanical system. With the engine mated to the frame, the motorcycle chassis is now placed onto the primary assembly line, an overhead conveyor system that moves each bike along a guided rail through multiple semi-automated workstations. The first station is the front suspension installation area. The H2R utilizes massive 43mm KYB AOS2 forks, which are fully adjustable and coated with a low-friction DLC layer. Each fork is filled with a precise volume of high-performance suspension oil using a vacuum fill station, then sealed and compressed to check for internal leaks. Once ready, the forks are inserted into the triple clamps and aligned using a digital laser alignment rig to ensure perfectly parallel orientation. Following this, the front wheel assembly, which consists of a Marchesini forged aluminum rim, dual 330mm Brembo discs, and a Pirelli slick racing tyre, is rolled up to the workstation. The wheel is mounted onto the axle, and the Brembo M50 monoblock calipers are installed with anti-vibration shims. The brake lines are routed along the fork legs using pre-formed clips, and each banjo bolt is torqued and marked with a color-coded paint pen for visual confirmation of completed steps. Parallel to the front suspension assembly, another robotic cell is preparing the swing arm sub-assembly. The H2R's single-sided swing arm is a hollow, forged aluminum unit with internal stiffeners. It is laser welded and then machined to accept the axle carrier and chain adjusters. Once verified for alignment using a 3D measurement gantry, the swing arm is connected to the frame using a solid pivot bolt, then connected to the rear shock. The rear suspension is a gas-charged KYB monoshock unit, also fully adjustable, and mounted on a rising rate linkage system for progressive damping under heavy loads. With front and rear suspension in place, the H2R is now a rolling chassis capable of supporting its own weight. At this point, the conveyor system gently lowers the motorcycle onto a rolling dolly with locking casters, freeing up the overhead rail for the next unit. The rolling chassis is pushed manually to the next station, the electronics and wiring harness integration bay. Unlike lower-tier motorcycles, where wiring is often installed as a single unified harness bundle, the H2R employs a modular wiring system. Multiple sub-harnesses for the engine control unit, traction control system, data logger, ABS system, and dashboard are installed independently, with each module having its own waterproof snap lock connector. The main harness is routed through the spine of the frame, secured with P-clips and thermal-resistant sleeves to protect from engine heat. Each connector is scanned using an RFID tool to ensure proper mating, and the system performs a low-voltage continuity check before proceeding. Once the electrical systems are routed, the control units are mounted in their designated locations. The inertial measurement unit is mounted beneath the seat. The ECU is housed in a vibration-isolated tray behind the headstock, and the quick shifter sensor is attached to the gear linkage rod. The dashboard, a full-color TFT display, is installed into the carbon fiber front cowl support and wired into the CAN bus network. With control systems in place, the next stage is the installation of the fuel system. The H2R's fuel tank is not merely a container, it is a shaped aluminum shell with internal baffles and foam inserts designed to reduce sloshing during extreme cornering. Each tank is pressure tested at 1.5 times normal operating pressure to check for leaks. A high-flow fuel pump is mounted internally, and the tank is lined with a corrosion-resistant coating that protects against ethanol degradation. The tank is installed onto rubber isolators on the frame spine and connected to the fuel rail via quick disconnect couplings. Underneath the fuel tank, the intake system comes together. The airbox is a sealed, high-capacity plenum chamber designed to handle pressurized air from the supercharger. It features a ram air intake duct and a high-flow air filter made from synthetic fibers. Sensors for intake air temperature and pressure are inserted, and the throttle bodies, ride-by-wire, electronically controlled units, are bolted directly to the intake ports. The supercharger outlet feeds directly into the airbox, and a blow-off valve is installed to regulate excess pressure during throttle closure. Once all intake and fuel connections are secured, the exhaust system is installed. The H2R utilizes a titanium exhaust header that is hand-welded and purge-welded from multiple conical sections. Each pipe is flow bench tested prior to assembly to ensure even back pressure across all 4 cylinders. The exhaust system includes a collector and a short, undertail silencer, designed to reduce weight and maintain optimal power output with minimal restriction. Sensors for oxygen content and exhaust temperature are threaded into the headers and linked to the ECU. At this point, the bike is fully assembled mechanically, but bodywork has not yet been applied. That comes in the next segment of the production process. But before that, the motorcycle moves into the first startup and diagnostic bay. Here, technicians connect a master diagnostic tablet to the ECU via the OBD port. The system runs a full checklist, verifying sensor functionality, fuel pump pressure, throttle actuator operation, and system voltages. Once verified, the bike is started for the very first time. This initial start is a tense and critical moment. The technician listens closely for any abnormal mechanical noise, monitors the idle speed, checks for warning lights on the TFT display, and ensures that oil pressure rises immediately upon startup. The engine is allowed to idle until it reaches operating temperature, during which time the cooling fan, radiator circulation, and combustion balance are all evaluated. Any deviation from spec prompts an immediate stop and transfer to the diagnostic cell for further investigation. If the startup test is successful, the motorcycle is shut down and moved to the fluid leak test station. Here, a UV dye is added to the oil and coolant systems, and the bike is placed under black light to reveal any possible leaks at hoses, joints, or gaskets. Pressure is applied to the cooling system using a sealed radiator cap rig, and the oil system is pressurized via a pneumatic pump. This ensures that even micro leaks are detected before the bike proceeds to final cosmetic assembly. With all functional systems now tested and verified, the powertrain mounted, the electronics integrated, and the fluids checked for sealing integrity, the Kawasaki Ninja H2R is finally ready to receive what many consider its most striking feature: its full carbon fiber bodywork. Unlike plastic fairings found on standard motorcycles, the H2R's aerodynamic surfaces are crafted entirely from pre-preg carbon fiber panels that are formed, trimmed, and finished in a tightly controlled composites facility within Kawasaki's aerospace division. Each carbon panel, from the sculpted front cowl to the aggressive side fairings to the single-piece tail section, begins life as a sheet of carbon fiber impregnated with epoxy resin. These sheets are hand-laid into CNC machined aluminum molds, layer by layer, with careful attention to fiber orientation and overlap. This layup process determines the final strength and stiffness of the component. And technicians follow a digital blueprint showing precisely where each ply must be placed. Once the layup is complete, the mold is vacuum sealed inside a heat-resistant bag and placed into an autoclave. In the autoclave, the part is subjected to high temperature and pressure, curing the resin and fusing the carbon plies into a single monolithic shell. The process takes several hours, during which the exact pressure and thermal cycle are carefully controlled and logged. After curing, the mold is cooled and the part is demolded and sent to the trimming station. Here, 5-axis CNC water jet cutters remove excess material and create mounting holes, while laser measuring arms verify dimensional accuracy down to fractions of a millimeter. Once trimmed, each body panel goes through a polishing and surface inspection process. Technicians in cleanroom suits buff the surface to prepare it for paint, but for the H2R, this isn't just a cosmetic paint job. It's a defining visual signature. The entire carbon shell is sprayed with Kawasaki's proprietary mirror finish paint, a multi-layered formula that gives the H2R its iconic black chrome look. This paint contains a layer of silver-infused base coat that reflects light like a mirror, followed by multiple layers of clear coat that are wet sanded and polished between applications. The painted carbon fiber parts are then cured in low dust ovens at carefully controlled temperatures. When they emerge, they undergo final inspection under polarized lighting to reveal any imperfections invisible to the naked eye. Only when each piece passes this inspection are they released to the final cosmetic assembly line. Back in the main assembly hall, the rolling chassis is now stationed at the fairing installation bay. Here, a team of 2 technicians works on each unit, using soft-gloved hands and non-marring tools to install the carbon fiber bodywork. The upper cowl is mounted first, secured to a lightweight subframe using vibration-resistant fasteners. The side fairings follow next, installed with grommeted bolts and lined with thermal insulation on the inner surfaces to protect against engine heat. The winglets, a defining aerodynamic element of the H2R, are bolted to the sides of the front fairing using precision jigs. These carbon fiber strakes generate downforce at high speeds and are carefully aligned to match the factory's computational fluid dynamics models. The tail section, which includes the seat pan and integrated rear lights, is installed last. It slots over the subframe like a precision machined cover, secured with hidden fasteners that leave the outer surface clean and uninterrupted. The final visual pieces include the windscreen, made of high-impact acrylic formed over a heated vacuum mold, and the mirrors, which are unique to the H2R in that they are replaced by aerodynamic blades due to its track-only designation. These aerodynamic devices further contribute to the overall downforce and high-speed stability of the motorcycle. With all external components now in place, the motorcycle advances to the lighting and display verification stage. Even though the H2R is not street legal and lacks conventional headlamps, it still features essential lighting systems for track use, including brake lights and dashboard illumination. A diagnostic terminal is connected once more to the onboard electronics, which triggers all LEDs, signal displays, and digital readouts. Any pixel dropout or timing issue in the TFT display is immediately flagged, and the dashboard is swapped out before the motorcycle proceeds. The next phase is torque auditing. Using a handheld digital wrench interface, a technician rechecks every critical fastener on the motorcycle, referencing a torque database specific to the H2R. Each bolt, from the engine mounts to the suspension linkages to the brake calipers, is checked, and the data is wirelessly transmitted to a central quality control server. This system creates a complete torque audit trail for every unit, ensuring that no component is under or over-tightened, which could lead to safety issues under track loads. Following torque audit, the motorcycle is moved to the final mechanical verification bay, a rolling road dynamometer enclosed in a safety chamber. Unlike the earlier engine dyno test, this test evaluates the entire drivetrain system, including wheel alignment, chain tension, gearbox operation, and traction control responsiveness. The motorcycle is strapped down securely onto a rotating drum, and a technician rides the bike through a simulated series of track laps using paddle inputs to shift gears, apply throttle, and trigger braking. The onboard IMU and traction control system are monitored in real time to assess how the electronic aids respond under aggressive load transitions. One particularly crucial part of this test is the quick shifter evaluation. The H2R uses a bidirectional quick shifter that allows for clutchless upshifts and downshifts under load. The dyno software simulates various throttle and RPM combinations while the technician triggers shifts. Sensors measure delay time between shift input and gear engagement, and the ECU adjusts the ignition and fuel cut profile dynamically. If lag or false neutrals are detected, the quick shifter sensor or shift drum is re-inspected. Following dyno verification, the motorcycle is shut down and allowed to cool under controlled airflow. It is then cleaned using ionized air to remove any dust or debris collected during testing and rolled into the inspection corridor, a quiet, well-lit area reserved for aesthetic and dimensional verification. Here, trained inspectors examine every square centimeter of the motorcycle's surfaces under fixed-angle lighting rigs that highlight reflections and contours. They check for paint consistency, panel fitment, fastener flushness, and emblem placement. The final inspection is concluded with a checklist signed by a master inspector who holds clearance to certify H2R units for packaging. A QR-coded certification tag is applied beneath the seat, containing digital records of every test, torque, spec, and visual check the motorcycle has passed. This tag remains with the bike for life, accessible by service centers and authorized Kawasaki technicians. At this point, the motorcycle is ready for crating and shipping, but before that occurs, a factory photographer captures high-resolution images of each unit for archival and legal purposes. These photos document the visual condition at the time of shipment and are stored alongside each VIN's production history. The H2R is then rolled into the final staging area, a climate-controlled packaging room where each motorcycle is carefully enclosed in a custom-built steel and wood crate. The front wheel is braced, the suspension compressed slightly with straps, and the bike is cocooned in protective foam. Every surface prone to scratching is wrapped with a low-tack film. Accompanying the motorcycle is a documentation pack that includes a certificate of authenticity, a technical user manual, a tuning guide, and the special tools required for trackside maintenance. Now ready for departure, the crated H2R is scanned into the logistics database and scheduled for dispatch. Its destination could be a private collector's garage, a professional racing team's paddock, or a high-end performance dealer specializing in exotic motorcycles. Once the Kawasaki Ninja H2R has been crated and logged into the factory's outbound inventory system, its journey through the global supply chain begins. The finished motorcycle, now nestled inside a reinforced steel-tubed crate with engineered shock absorption inserts and padded contact points, is not treated like standard inventory. This is not mass market production. Each unit is registered and scheduled for delivery with the same level of care typically reserved for aerospace-grade cargo or high-value prototype machinery. The H2R crate is fitted with a tamper-evident seal and a GPS-enabled tracking unit. This small battery-powered device is embedded in the crate frame and continuously broadcasts location, temperature, and shock readings throughout the duration of the shipment. The goal is absolute transparency and control. Kawasaki's logistics division uses a centralized tracking portal to monitor every H2R in transit, ensuring that any anomaly, a sudden temperature spike, an excessive tilt angle during forklift handling, or an unexpected deviation from a scheduled route triggers a real-time alert and investigation. Within the Kawasaki factory's outbound logistics terminal, All outgoing H2Rs are staged in a secure area awaiting carrier pickup. This area is isolated from regular shipping docks and utilizes biometric access controls. When transport is scheduled, only certified freight handlers are permitted to load the crated bikes onto specialized trucks equipped with air ride suspension systems. These vehicles reduce vibration and road shock that could otherwise stress the precision-fitted carbon components or delicate electronics inside the crate. Each transport vehicle is assigned a specific destination hub, most commonly one of Kawasaki's global distribution centers. These hubs, located strategically in Europe, North America, the Middle East, and Asia, are more than just warehouses. They are hybrid facilities combining bonded customs zones, climate-controlled storage, and dealer preparation stations, all operating under strict quality assurance protocols. When a truckload of H2R units arrives at one of these hubs, the unloading process is supervised by Kawasaki regional logistics managers. Each crate is inspected for seal integrity and then scanned into the regional inventory management system using the embedded RFID and QR codes. For units destined for overseas markets, international freight forwarding is used. Crates are loaded into secure ISO shipping containers fitted with humidity control packs and shock-damping floor mounts. These containers are then booked onto cargo ships under insured, high-priority manifests. During ocean transit, the environmental monitoring systems embedded in the H2R crates continue logging data, which is uploaded via satellite uplink every 12 hours. When the containers reach port, customs clearance is expedited through Kawasaki's import-export licensing system, which pre-registers each motorcycle's VIN with the appropriate government authorities to simplify the paperwork associated with limited use non-street legal vehicles. Once the motorcycles arrive at their respective dealer prep centers, they are again moved using air ride trucks and secured holding bays. The dealer-level uncrating process is perhaps one of the most sensitive moments in the entire chain. These centers are equipped with padded flooring, overhead cranes, and specialized unboxing stations designed specifically for ultra-high performance motorcycles. Each crate is disassembled manually, using torque-limited tools to avoid overstressing any fastener. The protective wrap and foam buffers are removed, and a technician conducts a full visual inspection before any mechanical interaction occurs. At this point, the motorcycle is still in a semi-dormant state. While fully assembled at the factory, the H2R is shipped with several systems disabled or set to low activation mode. For example, the ECU is placed in a transport-safe state to prevent any unauthorized ignition or tampering during transit. The traction control system and launch control features are also disabled until activation codes are entered through the factory diagnostic tablet. These codes are provided only to certified Kawasaki race dealer technicians who have completed a specialized training program exclusive to the H2R platform. The first step during dealer prep is to activate the motorcycle's electrical systems. A lithium-ion high-output battery, which was shipped separately to avoid power drain or risk of damage, is installed using a torque-calibrated battery tray mount. The diagnostic tablet is then connected, and the technician runs a software handshake that reactivates the ECU, initiates a full sensor sweep, and calibrates the electronic throttle bodies to their neutral closed position. This is followed by a firmware update if required, ensuring that the bike is running the latest version of Kawasaki's proprietary control logic, an intricate blend of traction, wheelie, slide, and launch control algorithms designed for elite track use. Fuel is then added to the tank, typically a high-octane, ethanol-free race blend sourced by the dealer. This ensures consistent combustion characteristics for the first startup under the dealer's supervision. The cooling system is topped off with pre-mixed long-life coolant, and brake fluid levels are checked. While all systems were previously pressure tested at the factory, this step ensures that nothing has been compromised during transport. The first dealer-level ignition is performed under controlled conditions. The motorcycle is mounted on a paddock stand with wheel chocks and exhaust ventilation systems in place. The technician initiates the ignition cycle, monitors the startup process, and allows the bike to idle while all systems reach operating temperature. During this time, the technician observes engine temperature, oil pressure, throttle responsiveness, and warning indicators. Once warmed up, the throttle is blipped to ensure proper response from the supercharger system. A high-pitched whine confirms that the planetary gear-driven supercharger is spinning freely, and boost sensors are checked to verify pressure increase under transient throttle input. Next comes dynamic system calibration. The dealer technician enters a closed test loop menu via the diagnostic interface, and the motorcycle performs a series of controlled internal tests. These include throttle plate synchronization, IMU pitch and roll calibration, wheel speed sensor checks, and brake pressure modulation trials. These diagnostic steps ensure that all ride assist systems are correctly aligned and functioning before the motorcycle is released to the client. Before final delivery, cosmetic detailing is performed. The bike is cleaned using non-reactive anti-static cloths and waterless detailing sprays to preserve the mirror finish. Tire pressure is adjusted to the recommended range for track delivery, and chain slack is fine-tuned based on the factory's specification under rider weight simulation. The data logging module, if the customer has opted for the full telemetry package, is also installed at this stage, including its GPS antenna and onboard SD card reader. At this point, the motorcycle is ready for customer delivery, but the H2R is not simply rolled out onto the sales floor. In most cases, the delivery is either performed at a private unveiling event or within a dedicated performance showroom, often involving customer briefings, technical walkarounds, and personalized instruction. The purchaser receives a digital service log, a registration keycard for the diagnostic system, and, depending on region, a certificate of ownership detailing the motorcycle's serial number and place of manufacture. Some customers even receive a titanium plaque etched with their VIN, engraved at the factory using the same fiber optic laser that marks engine components. For customers intending to race the bike, additional services are offered. These include initial track setup, suspension tuning based on rider weight and intended circuit, and ECU mapping optimization. Kawasaki certified race engineers are sometimes deployed directly to high-profile clients to help integrate the bike into a team's racing fleet or private collection. In total, from the moment an H2R begins its life in the alloy preparation bay to the moment it is fired up in a client's garage or paddock, the process spans multiple continents, dozens of specialists, and a series of rigorously enforced quality checkpoints. No step is accidental. Every decision, from the type of crate to the orientation of the brake lines during shipping, is designed to protect and preserve the uncompromising nature of the Ninja H2R. The journey starts as a concept long before steel meets the press or engines meet the chassis. Engineers and designers spend months, sometimes years, refining the blueprint of a model. Every curve of the bodywork, every mechanical component, and every safety feature is planned with meticulous care. It is not simply about designing something that looks appealing, but ensuring that every component can be manufactured reliably, assembled efficiently, and maintained for years of use. When the design is finalized, the preparation for production shifts into the realm of manufacturing engineering. This is where the physical requirements for building the car are translated into a sequence of processes, machines, and assembly operations. The factory layout is adjusted to accommodate new tooling and equipment. The stamping presses, welding robots, painting lines, and assembly stations are prepared in harmony, ensuring that the entire flow of production can move like a well-orchestrated symphony. Each department communicates with the others to align their timing, capacity, and technical requirements, because any mismatch between stages can create bottlenecks that slow the entire plant. Before we even see the first car body taking shape, we must understand the raw materials that feed this system. The backbone of every Suzuki vehicle is steel, but not just any steel. High-strength automotive steel sheets arrive from steel mills in giant coils, sometimes weighing over 20 tons each. These coils are delivered by rail or truck to the factory's stamping plant. Alongside steel, aluminum panels, plastics, resins, and a variety of other materials are delivered in a steady flow. The supply chain for a car factory is an ongoing pulse of incoming goods, timed precisely so that inventory storage is minimized. Many parts and sub-assemblies come from a network of suppliers that specialize in producing components such as seats, dashboards, headlights, and braking systems. Some of these suppliers operate right next door to the Suzuki plant in what is known as a supplier park to enable just-in-time delivery directly to the assembly line. The steel coils, once unloaded, are stored for only a short period before being moved to the stamping department. This is the first truly transformative stage of car manufacturing. In a cavernous hall filled with the rhythmic thunder of stamping presses, the steel sheets are uncoiled, flattened, and fed into enormous press machines. These presses exert thousands of tons of force, shaping the steel into the contours of fenders, doors, hoods, and roof panels. Each press operation uses dies, massive, precisely machined blocks of steel that mold the sheet metal into exact shapes. The dies can weigh several tons and are swapped out when changing to a different panel design. A single car body panel often requires several stages of pressing, beginning with a rough form in the first die, followed by progressively more refined shapes in subsequent dies, until the panel meets its exact specifications. During stamping, every millimeter matters. Automated optical inspection systems check the freshly pressed panels for surface defects, ripples, or dimensional deviations. Any panel that does not meet standards is set aside for recycling, its metal returned to the melting process to be reformed into new sheets. This reduces waste and ensures that only flawless panels proceed to the next stage. The next stop for these panels is the body shop, an enormous section of the plant where the raw pressed steel pieces come together to form the recognizable skeleton of a Suzuki car. Here, the air is filled with the bright sparks of robotic welding arms. The panels are loaded into large jigs and fixtures that hold them in precise alignment while robots perform spot welds. These welds fuse the panels together permanently, ensuring structural rigidity and safety. For a modern Suzuki, this stage is heavily automated, with banks of robots working in perfect synchrony. However, skilled human operators remain essential for overseeing the process, making adjustments, and performing welds in tight or complex areas where robots cannot easily reach. The construction of the car body, known as the body in white, follows a carefully choreographed sequence. The floor pan, which forms the base of the vehicle, is placed first. Side panels and door frames are aligned and welded onto it, followed by the roof, front, and rear sections. Cross members, reinforcements, and brackets are added in specific places to enhance crash protection and structural strength. Door openings are checked against strict dimensional tolerances to ensure that later, when doors are hung and adjusted, they will fit perfectly without rattling or misalignment. At various points in this body shop process, quality control engineers measure critical points on the structure using laser scanners and coordinate measuring machines. This prevents small errors from compounding into serious alignment issues later. The body in white, once fully welded, is a bare shell of gleaming steel. It has no paint, no trim, no glass, but its proportions and integrity are set for the rest of its life. Before painting, the bare metal body must be prepared meticulously. Even tiny traces of oil from stamping or dust from welding can cause paint defects. Therefore, the bodies are sent through a cleaning and pre-treatment line. They are dipped in a series of chemical baths that remove contaminants, apply a phosphate coating to improve corrosion resistance, and prepare the surface for paint adhesion. This pre-treatment line is fully enclosed, and the bodies are moved on an overhead conveyor through each tank, sometimes fully submerged, to ensure every crevice is treated. The final step in this stage is a drying oven that removes all moisture. Only then does the car proceed to the paint shop, a section of the factory that feels completely different from the noisy stamping or welding halls. Here, the environment is controlled for temperature, humidity, and cleanliness. Dust particles are the enemy of smooth automotive finishes, so the entire paint area operates with filtered air and positive pressure to keep contaminants out. The first layer to be applied is the electrophoretic primer, also called E-coat. The car body is immersed in a bath where an electric current causes primer particles to bond evenly to every surface, inside and out, including hard-to-reach cavities. Once the primer is cured in an oven, sanding robots and human operators smooth the surface before the application of the base coat, which provides the car's color. Depending on the model, Suzuki may use robotic spray arms that follow precise patterns to ensure even coverage, especially around edges and curves. After the base coat, a clear coat is applied to provide gloss and protect the color from ultraviolet damage and environmental wear. Each coat is baked at controlled temperatures to ensure hardness and adhesion. As the painted shells emerge from the curing ovens, they are inspected under powerful lighting in what is often called the light tunnel. This is a controlled environment where every curve of the car's surface is scrutinized by trained eyes and optical sensors for even the smallest imperfection. A speck of dust caught under clear coat, a ripple in the finish, or an uneven tone in the paint can be enough for a vehicle to be sent back for refinishing. In automotive manufacturing, these cosmetic checks are not mere vanity. They are essential to meeting customer expectations and protecting the long-term integrity of the finish. Only after passing these surface quality tests does the body proceed to what is known as the trim line. The trim line is the first phase where the car begins to be filled with the parts that make it functional and comfortable for passengers. The process is meticulously sequenced. Every car moving down the line has a build specification loaded into the plant's production system. This ensures that the correct color interior, optional features, wiring configurations, and mechanical components are installed at exactly the right point. Workers and automated equipment access the build information via monitors or handheld devices, so there is no guesswork about which parts to install. The first installations are typically sound deadening materials. Large sheets of insulating mat are fitted to the floor, inside the doors, and sometimes behind interior panels to reduce road and engine noise. Wiring harnesses are then routed through the body. These harnesses are pre-assembled bundles of wires that carry electrical signals to lights, sensors, power windows, and entertainment systems. Fitting them correctly is critical. Any pinched wire or poor connection can lead to costly troubleshooting later. Harnesses are secured with clips and ties to prevent movement or abrasion over years of use. While the wiring is being routed, HVAC ductwork is fitted, ensuring that heating and cooling air can reach every vent in the cabin. This is followed by the dashboard assembly, which is often delivered as a complete unit from a supplier. Installing a dashboard is a delicate maneuver, as it must align perfectly with mounting points while accommodating wiring connectors, instrument clusters, and control modules. A team of technicians guides it into place and secures it with fasteners that have specific torque requirements to avoid rattles or stress on the materials. Seats are another major interior installation. These arrive pre-assembled, complete with upholstery, cushioning, and any built-in electronics such as seat heaters or airbag modules. Using mechanical assists to avoid strain, workers position the seats in the cabin and bolt them to the floor mounts. Seat positioning is not only about comfort, it has to align with seatbelt anchor points and airbag deployment geometry for safety. Parallel to interior fitting, work begins on marrying the body to the mechanical heart of the car, the chassis, and drivetrain. This is a carefully timed coordination between two moving lines, one carrying the prepared body shells and another carrying the assembled underbody module, which includes the engine, transmission, suspension, exhaust system, and braking components. The underbody is prepared in a separate section of the plant, often referred to as the chassis line, where technicians and robots assemble the engine and transmission onto a subframe, attach the front and rear suspension assemblies, mount the exhaust system, and connect steering linkages. In the case of Suzuki's smaller passenger vehicles, these assemblies are designed to be compact yet easy to service, with many components integrated into modular subframes. This not only speeds up initial assembly, but also allows for easier maintenance during the vehicle's lifetime. The wheels and tires are sometimes fitted at this stage, though final torque on wheel nuts may be left until later in the process to account for transport considerations within the factory. The moment known as the marriage is one of the most striking in car assembly. The painted body shell is lifted slightly above the moving chassis assembly by a synchronized hoist system. As the chassis slides into position beneath the body, the two are lowered together, and a team quickly secures them with precision fasteners. At this point, the car's major structural integration is complete. The engine and drivetrain are physically connected to the body. Once married, the vehicle moves to stations where cooling lines, fuel lines, and electrical connections between the body and chassis are linked. This requires careful attention to routing, sealing, and securing. Every hose clamp, connector, and grommet is placed to avoid chafing or leaks, as even a small oversight here could lead to operational failures after delivery. The next focus is glazing, the installation of windows and windshields. Modern automotive glass is bonded to the body using high-strength urethane adhesives, which not only hold the glass in place, but also contribute to the vehicle's structural rigidity and crash performance. Before installation, the glass edges are treated for adhesion, and the body's window frames are cleaned and primed. Robotic applicators or skilled technicians lay a precise bead of adhesive, and the glass is positioned using vacuum lifters to avoid direct handling. Proper curing of this adhesive is critical, and vehicles are timed through the assembly process so that the bond sets before the car experiences any structural flex. After the glass is fitted, exterior trim pieces are added. These can include weather strips, side moldings, roof rails, and badging. The fit and finish of these components are critical to the car's perceived quality. Misaligned trim can create wind noise or water ingress, while inconsistent badging undermines visual symmetry. The doors, which may have been removed earlier for easier access during interior work, are now reattached. They are hung on hinges that allow for fine adjustment, ensuring consistent panel gaps and smooth operation. Once aligned, the doors receive their inner panels, window regulators, locks, and wiring for power accessories. The tailgate or trunk lid undergoes a similar process, with alignment checked to within millimeter tolerances. As the car progresses down the line, more systems come online. Fluids are filled: engine oil, transmission fluid, coolant, brake fluid, power steering fluid, and windshield washer solution. In many plants, these filling systems are automated to ensure precise volumes and to reduce spillage. The first electrical power-up occurs at this stage, allowing the vehicle's onboard computer systems to initialize. This is the moment where workers can begin testing electrical functions like lighting, wipers, and infotainment displays. Once the newly assembled Suzuki approaches the end of the main assembly conveyor, the atmosphere in the plant shifts from a building process to one of verification and fine-tuning. This is the beginning of the commissioning stage, where the focus moves from installing components to ensuring that everything functions exactly as intended. The car is no longer just a collection of parts. It is a complete vehicle that must now prove itself ready for the road. The first stop after major assembly is often the wheel alignment station. Here, the vehicle is placed on a set of precision plates and laser-guided measurement systems that check the angle of each wheel relative to the chassis and to one another. Proper alignment is critical for handling stability, tire wear, and driver safety. Adjustments are made using specialized tools that tweak the suspension's camber, caster, and toe settings until the readings fall within strict tolerances defined by Suzuki's engineering specifications. This step also ensures that the steering wheel will be centered when the car is driven in a straight line, preventing an issue that would be instantly noticed by a new owner. Following alignment, the car moves to the fluid check and topping station. Although fluids have already been added during earlier stages, they are now checked for correct levels and quality. Any air bubbles in hydraulic systems, such as the brakes or clutch, are purged through a process known as bleeding, ensuring consistent performance. Coolant systems are pressure tested to confirm there are no leaks, and the fuel system is primed and checked for tightness to avoid vapor or liquid escapes. Each of these checks is both a safety measure and a warranty safeguard, as fluid leaks can lead to early vehicle failures. Now comes one of the most anticipated moments in the factory, the first engine start. At a dedicated station, the technician inserts the ignition key or engages the start button, bringing the Suzuki's engine to life for the first time. This is not a ceremonial step, but a critical diagnostic event. As the engine runs, technicians listen for abnormal sounds, check for warning lights on the instrument cluster, and monitor the readouts from diagnostic equipment connected to the vehicle's onboard computer. The engine control unit records any fault codes during the first start, and these must be addressed immediately before the car can progress. This step also ensures that fuel delivery, ignition timing, idle control, and emission systems are functioning properly from the outset. Once the initial engine check is complete, the car enters what is called the rolling road test. This is essentially a dynamometer station built into the assembly line. The vehicle is driven onto large rollers, which allow the wheels to spin as though the car were traveling down an actual road. The technician operates the vehicle through various speeds and loads, while sensors measure engine output, drivetrain smoothness, and braking performance. Onboard equipment also checks that gear shifts are smooth in both manual and automatic transmissions, that traction control engages correctly, and that the ABS activates as designed during simulated stops. For hybrid or electric Suzuki models, the rolling road test verifies battery performance and regenerative braking operation as well. After this dynamic evaluation, the car undergoes an emissions test. The exhaust gases are captured in a sealed system connected to high-precision analyzers that measure the concentration of pollutants such as carbon monoxide, hydrocarbons, and nitrogen oxides. The results must comply with the regulations of the market where the vehicle will be sold. If any parameter is out of range, adjustments to the engine management software or mechanical repairs are made immediately. Emissions compliance is one of the most heavily regulated aspects of vehicle production, and no car can leave the factory without passing this check. With the mechanical and electronic systems validated, attention turns to the finishing area. This is where skilled technicians examine the entire vehicle for fit and finish issues. The car is inspected under bright lighting and from multiple angles to detect paint blemishes, uneven panel gaps, or imperfections in trim alignment. Special gauges are sometimes used to measure panel gaps to within fractions of a millimeter, ensuring consistency from one vehicle to the next. In addition to visual checks, technicians test all customer-facing features. Every switch, button, knob, and lever is operated to confirm proper function. Windows are raised and lowered, mirrors adjusted, wipers cycled, and climate control systems run through heating and cooling modes. Infotainment systems are powered up to verify screen clarity, touch sensitivity, and speaker output. Even less obvious features, like seat height adjusters and child safety locks, are tested to avoid customer dissatisfaction. The underbody of the car is also inspected at this stage, typically with the vehicle lifted on a hoist. Inspectors look for fluid leaks, loose fasteners, or improperly routed cables and hoses. Protective coatings applied to resist corrosion are checked for completeness, especially around weld seams and in wheel wells where road spray is most intense. Once all systems are confirmed, the car enters the water test booth. This is an enclosed chamber equipped with high-pressure spray nozzles that douse the vehicle from every direction for several minutes, simulating heavy rainfall and splash conditions. After the soaking, technicians climb inside to check for any water ingress around doors, windows, or the trunk area. Sealing defects are corrected immediately, as water intrusion can lead to electrical failures and interior damage over time. If the car passes all these stages, it proceeds to the final audit line. This is often staffed by some of the most experienced personnel in the factory, as they perform a comprehensive review of the vehicle. The final audit is essentially a condensed version of all earlier checks combined into a single process. It includes visual inspection, functional testing, and a short, low-speed road test within the plant grounds. Any fault, no matter how minor, is documented and corrected before the car can be released. Once signed off, the vehicle's identification and tracking information in the production database are updated to reflect that it has cleared manufacturing. Protective coverings are then applied to vulnerable areas like the hood, roof, and interior surfaces to prevent damage during transport. From here, the Suzuki moves into the dispatch yard, where cars are grouped according to their destination markets. Some are loaded onto specialized car transport trucks, while others are driven onto railway wagons designed for vehicle shipment. For export markets, vehicles are often taken to a port facility where they are driven into large car carriers, ocean-going ships, with multiple decks capable of holding thousands of cars. Throughout this entire process, Suzuki's production philosophy emphasizes continuous improvement. Every issue found during assembly or final inspection is logged in a central system, allowing engineering and quality teams to analyze trends and implement corrective measures. This feedback loop ensures that problems are addressed at their source rather than repeatedly corrected downstream. Once a Suzuki car has passed its final factory inspection and been fitted with protective coverings, its story shifts from manufacturing to logistics. This is a crucial and often underappreciated stage because even the most perfectly built vehicle must arrive at its final destination without damage, delay, or compliance issues. The dispatch yard of a Suzuki plant operates with the same precision as the assembly line itself, ensuring that each vehicle is correctly identified, grouped, and routed toward the market it is intended for. Vehicles are scanned into a tracking system using their vehicle identification number, or VIN, which serves as a unique fingerprint for each car. The VIN is tied to the car's exact configuration, model, trim level, color, engine type, and any special market-specific features. This tracking system communicates directly with Suzuki's global distribution network, allowing logistics planners to match production output to regional demand forecasts. The cars are arranged in neat rows within the yard, typically grouped by destination, so that loading can be performed efficiently. For domestic markets, the vehicles are usually transported by specialized car carrier trucks. These trucks are designed with hydraulic ramps that can be adjusted to accommodate multiple rows of vehicles, often up to 8 or 9 depending on size. Drivers are trained in securing the cars with wheel straps or chocks to prevent movement during transit. The loading sequence is carefully planned so that the first vehicles to be delivered are loaded last, minimizing handling at intermediate stops. For longer distances within the same country, rail transport is sometimes preferred. Trains can carry hundreds of vehicles in enclosed rail cars, protecting them from weather and debris. The loading process involves carefully driving each Suzuki up narrow ramps and into the railcar bays, with only centimeters of clearance on each side. Drivers in this operation are trained to maintain extremely slow, steady movement to avoid any accidental scrapes. The railcars are then sealed until they reach the unloading terminal, often located near major distribution centers. When cars are destined for international markets, the process becomes more complex. Export-bound Suzukis are loaded onto massive ocean-going vessels known as roll-on/roll-off ships, or RO-ROS. These ships function like floating parking garages, with multiple decks connected by internal ramps. Vehicles are driven aboard under their own power and parked in tight formation, with only enough space for mirrors and doors to avoid contact. Crews secure each car with wheel chocks and lashings to keep them stable during the voyage. Depending on the route, these ships can carry thousands of vehicles at once, stopping at several ports before reaching their final destinations. The voyage can last anywhere from a few days to several weeks, depending on the distance between the plant and the destination port. During this time, the vehicles remain sealed and untouched with their protective films and coverings intact. Because environmental conditions at sea can vary, including salt-laden air, the factory-applied coatings and transport wraps are specifically chosen to prevent corrosion or cosmetic damage. Once the ship reaches its destination port, a highly coordinated unloading operation begins. Teams of trained port drivers board the ship and drive the cars off in a continuous flow, following a pre-planned sequence. The cars are then parked in secure port storage yards, where customs clearance procedures are initiated. Every country has its own import regulations, and Suzuki's logistics team ensures that each vehicle's documentation, including emission certificates, safety compliance paperwork, and shipping manifests, is complete and accurate before customs inspection. After clearing customs, the vehicles are typically sent to a regional distribution center. Here, a process called pre-delivery inspection, or PDI, takes place. Although the car has already been tested extensively at the factory, the PDI ensures that nothing has changed during transport. Trained technicians remove protective coverings, inspect the bodywork for any transit-related damage, check all fluid levels, and verify that the battery is fully charged. Tires are inspected for correct pressure, and software updates may be installed if newer calibration files have been released since the car left the factory. This is also where market-specific adjustments are made. For example, vehicles shipped to countries with different lighting regulations might have headlight aim adjusted or daytime running lights enabled or disabled according to local laws. Navigation systems are loaded with the correct regional maps, and owner's manuals in the appropriate language are placed in the glove compartment. If a dealer has ordered optional accessories such as roof racks, spoilers, or upgraded infotainment units, these may be installed at the distribution center to avoid slowing down the main assembly line. Once PDI is complete, the cars are released for final transport to dealerships. Depending on geography, this may involve another short truck journey or additional rail transit. Dealers receive advance notice of incoming stock through Suzuki's dealer management system, allowing them to prepare showroom space and schedule customer handovers for pre-sold vehicles. When the cars arrive at the dealership, the process takes on a more personal dimension. Dealership staff conduct their own incoming inspection to confirm that the car is in perfect condition. Any final detailing, such as washing, waxing, or vacuuming is performed to ensure a showroom-ready presentation. Paper floor mats, seat covers, and steering wheel protectors are removed, revealing the untouched interior. If the vehicle is destined for immediate delivery to a customer, the dealership staff will carry out the handover procedure. This involves explaining the car's features, demonstrating controls, and answering any questions the customer might have about operation or maintenance. The VIN is registered in the dealership system along with the customer's details, marking the official start of the warranty period. From the customer's perspective, the journey begins the moment they take the keys. From the factory's perspective, however, the cycle never truly ends. Feedback from dealerships about customer experiences, warranty claims, and any recurring issues flows back to Suzuki's engineering and manufacturing teams. This closed-loop communication helps identify opportunities for product improvements, process refinements, and supplier quality enhancements. Interestingly, the logistics chain is also part of Suzuki's environmental strategy. Modern vehicle transport planning aims to minimize unnecessary mileage and fuel use, sometimes even consolidating shipments from multiple manufacturers onto the same vessel or rail line to reduce emissions. In some markets, Suzuki works with dealerships to arrange bulk deliveries that reduce the number of trips and associated carbon footprint. In global terms, the distribution network is as critical to Suzuki's reputation as the production line itself. A flawless manufacturing process can be undermined by mishandled shipping, customs delays, or damage in transit. This is why Suzuki invests heavily in both technology and training to ensure that from the moment a vehicle leaves the assembly line until it arrives in the customer's driveway, it remains in the same pristine condition it was in at the final factory inspection. While the sight of finished Suzuki vehicles streaming out of the plant toward dealers and customers is the most visible sign of success, the real heartbeat of the company's manufacturing prowess lies in what happens behind the scenes. The precision of assembly, the timing of parts deliveries, and the consistency of quality all trace back to an intricate web of engineering coordination, supply chain management, and production system design. This interconnected system is what allows Suzuki to produce vehicles in large volumes without sacrificing the meticulous detail that defines a well-made car. The cycle begins long before the first sheet of steel is pressed, with engineering teams designing every component to be not only functional but manufacturable. This is known as Design for Manufacturability, or DFM. The aim is to ensure that parts can be produced consistently, at the right tolerances, and installed efficiently on the assembly line. For instance, a bracket might be designed with built-in alignment features that allow it to snap into place in only one orientation, eliminating the possibility of incorrect installation. Even the routing of a wiring harness is planned to minimize the number of bends and attachment points, reducing both assembly time and the risk of damage. This level of planning requires intense collaboration between product design engineers, manufacturing engineers, and even supplier representatives. Suppliers are involved early in the process to provide feedback on material selection, forming methods, and cost implications. A headlight supplier, for example, might work directly with Suzuki's styling team to adapt a design so that it can be assembled with fewer screws or clips, speeding up installation on the trim line. These interactions happen months, often years, before a model reaches production. Once the design is frozen, Suzuki's manufacturing engineers turn their attention to the factory itself. Every model introduction requires a detailed assessment of the production line layout, tooling, and automation requirements. This might involve installing new welding jigs for body panels, programming robots for different spray patterns in the paint shop, or creating custom assembly fixtures for unique components. Retooling a line is a massive undertaking, often done during scheduled downtime, to avoid disrupting ongoing production of existing models. One of the most critical decisions at this stage is determining the level of automation versus manual labor for each process. Suzuki, like many automakers, uses robots extensively for operations that demand absolute consistency, such as spot welding, seam sealing, and paint application. Robots excel at repetitive, high-precision tasks, and their ability to work in hazardous environments, like the fumes of a paint booth, improves worker safety. However, there are many tasks where human skill remains unmatched. Complex interior installations, final fit adjustments, and quality inspections often rely on trained technicians whose judgment and dexterity can adapt to small variations. For example, adjusting a door to achieve a perfect gap relative to the body involves subtle manipulation that a robot cannot yet match with the same flexibility. Suzuki's philosophy tends to blend automation with human oversight, creating hybrid workstations where robots perform the heavy lifting and humans ensure the final finesse. To keep everything running smoothly, Suzuki employs just-in-time manufacturing principles. This means parts arrive at the assembly line precisely when needed, rather than being stockpiled in large quantities. The benefit is reduced inventory costs and the ability to respond quickly to changes in demand. But this also requires a flawless supply chain, where every supplier delivers exactly on schedule. Any delay, whether from a parts plant, a transportation breakdown, or a customs holdup, can halt the entire assembly line within hours. To mitigate this, Suzuki maintains contingency plans and sometimes dual sources critical components so that production is less vulnerable to disruptions. The flow of materials within the factory is another area of intense engineering attention. Components are often delivered in sequenced racks, arranged in the exact order they will be installed. This eliminates the need for workers to search for the correct part, shaving seconds off each installation and reducing the risk of mistakes. In high-volume areas like the trim line, these seconds add up to major efficiency gains over the course of a day. Information flow is just as important as material flow. The entire production line is governed by a manufacturing execution system that tracks each vehicle in real time. As a body shell enters the assembly line, its VIN is scanned, and its build sheet is instantly displayed at every station it will pass. This ensures that workers and robots alike install exactly the right parts for that specific configuration. If the car is a right-hand drive model bound for the UK, for instance, the dashboard station will receive the corresponding layout and components. This tight integration between engineering design, supply chain logistics, and shop floor operations is what allows Suzuki to handle multiple models on the same assembly line. A plant might be building compact hatchbacks, sedans, and SUVs in a mixed sequence, with each vehicle requiring slightly different parts and assembly steps. Without advanced planning and flexible tooling, this kind of mixed model production would be chaotic. Instead, it runs as a coordinated rhythm, with each workstation adapting to the next vehicle as it arrives. Suzuki also invests heavily in continuous improvement through Kaizen, a philosophy of making incremental changes to enhance efficiency, quality, and safety. This means that every worker on the line is encouraged to suggest improvements, no matter how small. A simple change in the shape of a parts bin or the angle of a work platform can reduce strain, prevent errors, or shave time from a process. These changes are documented, evaluated, and, if effective, standardized across the production line. Quality control is embedded at every stage, not just at the end. Inline inspection stations use laser scanners, vision systems, and torque sensors to verify that parts are installed correctly and that critical dimensions are within tolerance. If a defect is found, the car can be diverted to an offline repair bay for immediate correction. This prevents issues from traveling further down the line where they would be more difficult and costly to fix. Equally important is the feedback loop between manufacturing and product engineering. When recurring assembly difficulties or component defects are identified, this information is relayed back to the design teams. They can then modify the design or manufacturing process to prevent the issue in future builds. For example, if a clip securing a wiring harness is found to be difficult to engage consistently, the design might be altered to make it more forgiving during installation. In essence, Suzuki's manufacturing ecosystem is a continuous conversation between design, production, and logistics. Each element shapes and supports the others, creating a tightly knit system capable of turning raw materials into road-ready cars at scale. It is this deep integration that allows Suzuki to maintain both cost efficiency and the reliability that customers expect.